Welcome to the Sleepy Scientist. It's wonderful to have you here. Before settling into tonight's question, perhaps take a moment to notice where you are. Maybe you're tucked beneath a blanket, listening in a dim room. Maybe you're on a quiet journey home, watching lights move past the window. Or maybe you're simply resting somewhere peaceful, letting the day loosen its grip a little. Wherever this finds you, hopefully you're warm, comfortable, and ready to let your thoughts wander gently upward. If these calm journeys through science help you unwind, a like and subscribe is always deeply appreciated. It helps this sleepy little corner of the internet keep drifting along, and if you're already subscribed, thank you, truly. Your support gives these quiet explorations a place to keep growing. Now, tonight's topic may sound a little alarming at first, but there's no need to panic. Earth is not about to misplace its magnetic field like a set of keys down the back of the sofa. But imagining what would happen if it disappeared can reveal just how much this invisible shield quietly does for us. From guiding compass needles to protecting satellites, softening the effects of solar storms, and helping keep the upper atmosphere from being quite so exposed to space. So let's begin, shall we? What if Earth's magnetic field disappeared, and the planet suddenly had to face the sun without its invisible armour? Earth does not usually feel like a planet with a shield around it. Most of the time, it feels open. The sky stretches above the rooftops, clouds slide quietly across the blue, sunlight spills over fields and streets, and at night the stars appear in the dark as if nothing stands between this world and the rest of space. From the ground there is no obvious wall, no glowing border, no great protective shell humming above the atmosphere. There is just air, weather, light, and the familiar feeling of being on solid ground. But Earth is not as exposed as it looks. Wrapped around the planet is a magnetic field, an invisible structure that begins deep below the surface and reaches far out into space. It is easy to think of this field as something that only matters to compass needles, because that is the version most people meet first. A small magnetized needle turns. It settles toward magnetic north. A map suddenly becomes more useful, and a walk through unfamiliar woods becomes slightly less likely to become an accidental survival documentary. But the compass is only the smallest hint of something much larger. Earth's magnetic field is not just a navigation tool, it is part of the planet's protection system. It is generated by motion in the liquid outer core, where iron-rich material moves under enormous heat and pressure. Far beneath oceans, continents, forests, cities, and sleeping houses, electrically conducting metal is in slow, restless motion. That motion helps create the magnetic field that surrounds the planet. The full process is known as the geodynamo, and it links the deepest interior of Earth to the space far above it. That connection is one of the strangest and most beautiful facts about this world. Something happening thousands of kilometers below your feet affects how Earth meets the sun. The ground may seem still, the night may seem quiet, yet deep inside the planet, movement in molten metal helps build an invisible boundary against the charged particles that stream through space. The magnetic field does not form a hard shell. It is not a science fiction force field, neatly glowing blue whenever danger arrives. It does not block everything, and it does not make Earth separate from space. Instead, it shapes the movement of charged particles around the planet. Far above the atmosphere, Earth's magnetic influence creates a region called the magnetosphere. This is the vast area where Earth's magnetic field strongly affects how charged particles behave. The magnetosphere is not perfectly round. On the side facing the sun, it is pushed inward by the pressure of the solar wind. On the side facing away from the sun, it stretches far behind Earth into a long magneto tail, a little like an invisible wake trailing behind a boat. Except the boat is a planet, the ocean is near Earth space, and the wake is shaped by magnetism rather than water. Space, as usual, takes a simple image and then makes it enormous. The reason this matters is that the sun is not a calm lamp hanging politely in the sky. It may look gentle from here, especially through a warm window in the morning, but the sun is an active star. It constantly releases energy, light, heat, magnetic disturbances, and a stream of charged particles called the solar wind. This solar wind is made mostly of protons and electrons, along with smaller amounts of other particles, flowing outward through the solar system at hundreds of kilometers per second. Earth moves through that flow all the time, not only during solar storms, not only during rare dramatic events. Every ordinary day while people are making breakfast, missing buses, answering emails, or wondering why one sock always disappears in the wash, the planet is travelling through a stream of particles from the sun. The magnetic field helps manage that meeting. It deflects and redirects many charged particles before they can plunge directly into the upper atmosphere. Some particles are guided toward the polar regions, where they can collide with atoms and molecules high above the surface. Those collisions create auroras, the shimmering curtains of light seen near the poles. Auroras are beautiful, but they are not just decoration. They are visible signs of Earth interacting with space. If Earth's magnetic field disappeared, the result would not be instant planetary destruction. The oceans would not vanish in a day. The atmosphere would not be peeled away like wrapping paper. People standing at sea level would not suddenly be exposed to raw space. Earth's atmosphere is itself a powerful shield, thick enough to absorb and scatter many forms of radiation before they reach the ground. That layer of air does an enormous amount of quiet work. But losing the magnetic field would still matter deeply. The consequences would arrive in layers. The first problems would likely be felt by technology and people above much of the atmosphere's protection. Satellites would become more vulnerable to energetic particles that can damage electronics, disrupt signals, degrade solar panels, and shorten mission lifetimes. Astronauts would face greater radiation risks, especially during intense solar activity. Communications and navigation systems could become less reliable, not because every machine would instantly fail, but because the environment around Earth would become harsher and more unpredictable. Power grids on the ground could also face greater stress during major space weather events. When the sun sends powerful disturbances toward Earth, changes in magnetic conditions can induce electrical currents in long conductors, including power lines. Modern civilization depends on long connected systems, and long connected systems are very good at turning distant solar activity into very practical headaches. The sun does not need to know about transformers to be rude to them. The upper atmosphere would also be more exposed. Charged particles could interact more directly with atmospheric gases, influencing chemistry and heating in ways that scientists would need to model carefully. Over very long periods, a weaker or absent magnetic shield could make atmospheric loss to space easier. That does not mean Earth would quickly become Mars. Planetary atmospheres depend on many things, including gravity, temperature, chemistry, geology, volcanic activity, oceans, and the strength of the solar wind. But the magnetic field is one important part of that wider story. This is why organisations such as NASA and the European Space Agency study Earth's magnetic environment so carefully. Spacecraft monitor the sun, the solar wind, the magnetosphere, the ionosphere, and the radiation belts around Earth. Space weather forecasting is not a futuristic hobby. It is part of protecting satellites, astronauts, communications, aviation, navigation, and electrical infrastructure. The modern world reaches upward into space in more ways than it usually notices, and that is the quiet surprise at the heart of Earth's magnetic field. It belongs to both deep time and daily life. It comes from the planet's interior, from the movement of molten metal far below the surface, yet it helps protect spacecraft far above the atmosphere. It helps shape auroras, guide compasses, influence animal navigation, and soften Earth's encounter with the solar wind. It links geology, astronomy, technology, biology, and climate into one invisible system. From the ground, nothing about this is obvious. A person can stand beside the sea, or under trees, or in the ice, middle of a city at night, and feel only the ordinary world. Air on the skin, gravity under the feet, the faint glow of the sky. But above that ordinary scene, Earth's magnetic field is quietly at work. It is not perfect. It is not unchanging. It is not the only reason this planet is habitable. But it is one of the hidden conditions that helps keep Earth more sheltered than it would otherwise be. If it vanished, the planet would not instantly end. The story would be slower, stranger, and more layered than that. Satellites would suffer first. Astronauts would need more protection. Auroras might spread in unfamiliar patterns. Compasses would lose their ancient usefulness. Some animals could lose an important navigational sense. The upper atmosphere would face a rougher relationship with the sun, and over long spans of time, Earth would become a more exposed world. The magnetic field is easy to ignore because it is invisible. Yet many of the most important parts of nature are like that. They do not announce themselves loudly. They do not need to. They simply shape the conditions in which everything else happens. Earth's magnetic field is one of those quiet forces, born in the depths, stretched into space, standing between a living planet and the restless star it orbits. To understand why Earth has a magnetic field at all, it helps to travel downward in imagination, away from the sky, away from satellites and auroras, and into the planet itself. The shield around Earth does not begin in space. It begins far below the surface, in a hidden region of heat, pressure, metal, and motion. Earth is made of layers. The outermost layer is the crust, the thin rocky skin beneath continents and oceans. It feels enormous from a human point of view, because mountains, valleys, coastlines, cities and seabeds all belong to it. But compared with the whole planet, the crust is delicate, more like the skin on warm custard than the thick shell people might imagine. Beneath it lies the mantle, a vast region of hot, slowly flowing rock. The mantle is solid, but over very long spans of time it behaves in a way that allows movement, carrying heat upward and helping drive plate tectonics at the surface. Below the mantle is the core, and this is where Earth's magnetic story becomes especially interesting. The core has two main parts. There is a solid inner core, made mostly of iron and nickel, sitting at the centre of the planet under crushing pressure. Around it is the liquid outer core, also rich in iron and nickel, but hot enough and under the right conditions to move as a liquid metal. This outer core is roughly 2,200 kilometers thick, which is an absurdly large distance to hide beneath everyday life. A kettle may feel dramatic when it boils, but Earth has been quietly managing a deep metallic engine for billions of years. The liquid outer core is electrically conductive. That detail matters enormously. When electrically conductive material moves, it can generate electric currents. Electric currents can produce magnetic fields. In Earth's case, the motion of liquid metal in the outer core helps generate and sustain the planet's magnetic field through a process called the geodynamo. This is the central scientific idea behind how Earth makes its magnetism. The field is not painted onto the planet from outside. It is not left over like an old cosmic sticker. It is continually produced from within. The geodynamo theory became a major part of 20th century geophysics through the work of scientists including Walter M. Elsasser and Edward Bullard. Elsasser helped develop the idea that motion in Earth's electrically conducting core could maintain the magnetic field. Bullard also made important contributions to understanding how the dynamo process might work inside the planet. Their work helped turn Earth's magnetism from a mysterious planetary feature into something that could be studied through physics, mathematics, geology, and observation. But the geodynamo is not a simple machine with neat spinning parts. It is not like a bicycle dynamo attached to a wheel, except unfortunately buried under the mantle where nobody can reach it with a spanner. The outer core is turbulent, complex, and deeply inaccessible. Scientists cannot drill into it. The deepest human-made boreholes only scratch the crust. The core must be studied indirectly, through seismic waves from earthquakes, laboratory experiments, computer simulations, magnetic measurements, and the behavior of Earth's field over time. The movement in the outer core is driven partly by heat escaping from Earth's interior. Earth still holds heat from its formation. When the young planet grew through collisions and gravitational compression, it also contains heat from radioactive decay inside the planet. As heat moves outward, it helps drive convection, where hotter material rises and cooler material sinks. In the liquid outer core, this creates motion in the molten iron-rich fluid. Another important source of motion comes from the growth of the solid inner core. As Earth slowly cools, some liquid iron at the boundary of the inner core freezes and joins the solid center. This process releases heat and also leaves behind lighter elements in the surrounding liquid, helping stir the outer core through both thermal and compositional convection. In other words, the outer core is moved not just by temperature differences, but also by differences in composition and density. The planet is not merely hot inside. It is sorting, cooling, crystallizing, and stirring itself at the same time. Earth's rotation then helps organize this motion. Because the planet spins, moving fluids inside it are influenced by the Coriolis effect. The Coriolis effect is the same broad principle that helps shape large-scale patterns in Earth's atmosphere and oceans, including the rotation of major storm systems. In the core, it helps guide the motion of molten metal into long, organized patterns that can support a global magnetic field. Without rotation, the motion might still occur, but it would not be arranged in the same way. Earth's spin gives the deep metallic flow a kind of structure. The result is a magnetic field that extends from the core through the mantle and crust and far into space. It has a shape that is often roughly described as dipole, meaning it behaves in a broad sense like a giant bar magnet tilted inside the planet. But this is only a useful simplification. Earth's magnetic field is not perfectly neat, and it is not perfectly stable. It has smaller regional features. It shifts, it weakens and strengthens. Magnetic north drifts across the Arctic over time. The field has even reversed many times in Earth's geological past, with magnetic north and magnetic south swapping places. This makes the field feel almost alive, though it is not alive in the biological sense. It is dynamic. It is a process rather than an object. A compass needle may make it seem fixed, as if the planet has one permanent direction stamped into it forever. But the real field is constantly being regenerated by deep motion. Its shape changes because the flows in the outer core change. Its strength varies because the geodynamo is not perfectly steady. Its direction can wander because Earth's interior is not a quiet, symmetrical clock. That is one of the most important ideas to hold on to. Earth's magnetic field is not simply there. It is being made. Every moment deep beneath the ground, the planet is converting internal heat, metallic motion, electrical conductivity, and rotation into a magnetic environment that reaches into space. The same world that seems so calm from the surface is far below, restless enough to build an invisible shield. and this hidden engine matters because everything that happens higher up depends on it. The magnetosphere, the radiation belts, the behavior of auroras, the shielding of satellites, and the way Earth meets the solar wind all trace back to the geodynamo. A field surrounding the planet is really the surface expression of a deep planetary process. It is geology reaching outward until it becomes space weather. So when imagining Earth without its magnetic field, the true question is not only what would happen above the atmosphere, it is also what would have changed below the surface. For the field to disappear, the deep motion that sustains it would have failed, weakened, or reorganized in some extraordinary way. The shield in space is only the visible consequence, at least to instruments, of a much deeper story. Earth's magnetic field begins in darkness, in a place of metal and pressure, where the planet quietly turns its own interior motion into protection. Earth's magnetic field begins in the depths, but it does not stay there. It rises through the planet, passes through rock and ocean and atmosphere, and reaches outward into space, where it becomes something much larger than a compass-making influence. Around Earth, the field forms a vast region called the magnetosphere. The magnetosphere is the area around the planet where Earth's magnetic field controls the motion of many charged particles. It is not a solid bubble, not a glassy shell, and not a perfect wall. It is more like a moving boundary, shaped by the planet from within and shaped by the sun from without. Inside it, charged particles tend to follow the influence of Earth's magnetic field. Outside it, the solar wind has greater control. The edge between these regions is not quiet. It is a place of pressure, motion, and constant negotiation between a planet and its star. To picture the magnetosphere, it helps to remember that space near Earth is not empty in the simple sense. It may be vastly emptier than the air in a room, but it is not nothing. It contains particles, radiation, magnetic fields, and streams of plasma. Plasma is often called the fourth state of matter. It is a gas-like state in which atoms have been separated from some of their electrons, leaving a mixture of charged particles. The sun is made of plasma, and it sends plasma outward through the solar system all the time. This outward flow is called the solar wind. It is a continuous stream of electrons, protons, and other charged particles moving away from the sun at hundreds of kilometers per second. It does not arrive like ordinary wind because there is no air between the sun and Earth. Instead, it is a flow of electrically charged matter, carrying the sun's magnetic influence outward across interplanetary space. Earth is always inside this flow, just as a stone in a river is always meeting moving water. The idea of the solar wind was developed in the 20th century by the astrophysicist Eugene Parker. At the time, the idea that the sun was constantly blowing material into space was not immediately accepted by everyone. It sounded bold, partly because the sun had long been imagined as sending out light and heat, not as continuously filling the solar system with a stream of charged particles. Parker's theory predicted that the sun's outer atmosphere, called the corona, should expand outward into space. Later spacecraft measurements confirmed that this solar outflow was real. The sun was not merely shining, it was breathing particles into space, endlessly and powerfully. When the solar wind reaches Earth, it runs into the magnetosphere. The collision is invisible to the eye, but enormous in scale. On the side of Earth facing the sun, the solar wind presses the magnetosphere inward. This sun-facing region is called the day side. There, the magnetosphere is compressed, squeezed closer to the planet by the pressure of incoming particles and magnetic fields carried from the sun. The outer boundary, called the magnetopause, marks the region where Earth's magnetic influence and the solar wind pressure meet. On the opposite side, away from the sun, the magnetosphere is stretched far behind Earth into a long magnetotail. This nightside tail can extend for a vast distance into space, far beyond the orbit of the Moon during some conditions. It is a graceful and slightly strange thought. Earth carries a long magnetic wake behind it as it moves through the Sun's outflow. The planet does not simply sit in space like a marble. It carves a shape through the solar wind with a compressed front and a trailing tail, like an invisible windsock the size of a world. But the magnetosphere does not stop every particle. It is not a flawless umbrella, and the solar wind is not politely waiting outside. Some particles enter, some are redirected. Some become trapped. Some are guided along magnetic field lines toward the polar regions, where they interact with the upper atmosphere and help create auroras. This is why auroras are most often seen near the Arctic and Antarctic. Earth's magnetic field funnels charged particles toward high latitudes, where oxygen and nitrogen high in the atmosphere glow after being struck by energetic particles. That glow is beautiful, but it is also evidence. An aurora is not just a pretty curtain in the sky. It is a visible sign that charged particles from space are being channeled by Earth's magnetic environment. The magnetosphere protects by redirecting, absorbing, storing, and reshaping incoming particle energy. It does not make the solar wind disappear. It changes the way Earth receives it. One of the most important discoveries in this region came at the beginning of the space age. In 1958, the American physicist James Van Allen helped lead the scientific investigation aboard Explorer 1, the first successful United States satellite. Explorer 1 detected zones of intense radiation around Earth. These regions became known as the Van Allen radiation belts. They are areas where energetic particles are trapped by Earth's magnetic field, spiraling along magnetic field lines and bouncing between northern and southern regions. The Van Allen radiation belts are not simple rings like neat hoops around a toy planet. They are dynamic regions whose shape, intensity, and particle populations can change with solar activity. They contain charged particles, including energetic electrons and protons, held in place by Earth's magnetic field. For satellites and astronauts, these belts matter greatly. A spacecraft passing through regions of intense radiation must be designed with protection in mind. Electronics can be disrupted, sensors can be affected, and human bodies need shielding from excessive exposure. This is another way the magnetosphere is not just a shield, but a system. It deflects some charged particles, traps others, and channels some into the atmosphere. It creates zones of hazard as well as zones of protection. Space around Earth is not a calm, empty hallway between the planet and the Moon. It is structured by magnetism, filled with moving particles and constantly stirred by the Sun. The magnetosphere also changes from day to day. During calmer solar conditions, it may remain relatively stable. During stronger solar storms, when the Sun releases bursts of energy and material, the magnetosphere can become disturbed. The magneto tail can store energy and release it. The auroras can brighten and spread. Radiation belts can intensify. Satellites may need to enter protective modes. Radio signals can be affected. Power systems on the ground may feel the consequences through geomagnetic disturbances. The magnetic field may be invisible, but its behaviour can reach into very practical parts of modern life, and all of this traces back to the deep interior of Earth. The liquid outer core generates the magnetic field. That field rises outward and forms the magnetosphere. The magnetosphere meets the solar wind. The solar wind carries particles from the Sun. Those particles shape auroras, disturb satellites, and help define the space environment surrounding the planet. A motion in molten metal far below the crust becomes a protective shape far above the atmosphere. That is the remarkable chain of connection. The ground beneath your feet and the charged wind from the Sun are part of one continuous story. Earth's magnetic field is not merely a local feature of the planet. It is the way Earth reaches into space and negotiates with its star. Without the magnetosphere, the planet would not instantly lose everything. But it would meet the solar wind much more directly. The boundary would weaken. The flow of particles would become harder to manage. The invisible architecture around Earth would no longer stand between the atmosphere and the restless stream of the sun. To imagine Earth's magnetic field disappearing, the first thing to do is remove the movie version of the idea. There would be no single moment when the sky cracked open, the oceans began to steam, and every compass needle spun dramatically before giving up on life. The disappearance of Earth's global magnetic field would be serious, but it would not be instant planetary destruction. It would be a change in exposure. The planet would still turn. The air would still surround it. The oceans would still lie heavy in their basins. Gravity would still hold the atmosphere close. People on the ground would not immediately feel space reaching down to tap them on the shoulder, which is fortunate because space has famously poor bedside manner. The scenario being imagined here is also different from the magnetic changes Earth has experienced naturally throughout its history. Earth's magnetic field has weakened, strengthened, wandered, and reversed many times. During a geomagnetic reversal, magnetic north and magnetic south swap places over long geological timescales. These changes do not happen like a light switch. They unfold over thousands of years, with the field becoming more complicated and sometimes weaker before settling into a new arrangement. The sudden disappearance of the global field would be far more extreme than a normal reversal. It is a thought experiment, not a prediction of what is about to happen next Tuesday. That distinction matters because the real Earth is not heading toward a simple, immediate loss of magnetism. The magnetic field changes constantly, and magnetic north moves over time, but change is not the same as disappearance. A weakening field, a drifting pole, a regional oddity such as the South Atlantic anomaly, and a total loss of the global magnetic shield are not all the same event. They belong on the same broad scientific map, but they are not the same destination. If the global magnetic field vanished, the most immediate changes would occur above most of the atmosphere. Satellites would feel the difference quickly. Astronauts would face higher radiation risk. The upper atmosphere would interact more directly with charged particles from the sun. Auroras might appear in stranger places or become less neatly tied to the polar regions. Compass navigation would become useless because there would no longer be a stable global magnetic field for a compass needle to follow. Power grids could become more vulnerable during major space weather events, especially when solar activity disturbed the near-Earth environment. But the atmosphere would not instantly vanish. This is one of the most important points. Earth's air is not held in place by magnetism. It is held mainly by gravity. The magnetic field helps protect the upper atmosphere from some interactions with the solar wind, but it is not the thing preventing the whole atmosphere from floating away each morning like an irresponsible balloon. Earth is massive enough for its gravity to hold a substantial atmosphere, and that would still be true if the magnetic field disappeared. The atmosphere is also a powerful shield in its own right. At sea level, people are protected by many kilometers of air above them. Incoming particles and high-energy radiation must pass through that air before reaching the ground. Along the way, many are absorbed, scattered, slowed, or transformed into secondary particles. This is why astronauts in orbit face a much harsher radiation environment than someone sitting safely on Earth with a cup of tea and a suspiciously determined biscuit. The magnetic field matters greatly, but the atmosphere does a great deal of the shielding for surface life. This is why the consequences would arrive in layers. In the short term, The first major problems would be technological and orbital. Satellites would become more exposed to energetic particles that can interfere with electronics, damage components, and increase the risk of faults. Spacecraft are already designed with radiation in mind, but a planet without a strong magnetosphere would make the environment around Earth less forgiving. Navigation systems, communication satellites, weather monitoring spacecraft, and scientific observatories could all become harder to operate reliably. Human spaceflight would become more difficult as well. Astronauts aboard orbital stations already live with increased radiation exposure compared with people on the ground. Without Earth's magnetic field, that exposure would rise, especially during bursts of solar activity. Missions would need stronger shielding, better warning systems, and more cautious planning. Space would not become unreachable, but it would become more demanding, less comfortable, and even less interested in making things easy. On the ground, the effects would be less immediate, but not irrelevant. During powerful solar storms, changes in Earth's magnetic environment can induce electrical currents in long conductors, such as power lines and pipelines. Without the normal magnetic structure around Earth, the way these disturbances reach the planet could change. Power grids might need stronger protection, better forecasting, and more careful management. Modern civilization is deeply connected, and connected systems can be surprisingly sensitive to disturbances that begin 150 million kilometers away at the Sun. Biology would also respond unevenly. Most surface life would not suddenly die, because the atmosphere, water, soil, shelter, and biological repair mechanisms provide layers of protection. But some animals use Earth's magnetic field as part of their navigation. Migratory birds, sea turtles, salmon, and other creatures may rely on magnetic cues, alongside light, smell, stars, currents, and landmarks. If the global field vanished, those species would not necessarily become helpless, but some journeys could become more difficult, especially for animals that use magnetic information during long migrations or early life stages. The long-term consequences would be slower and more uncertain. Over thousands, millions, or even longer spans of time, a missing magnetic field could make the upper atmosphere more vulnerable to erosion by the solar wind. Atmospheric escape is the process by which atoms and molecules are lost to space. It happens on many planets, and it depends on several factors: gravity, temperature, atmospheric chemistry, solar activity, volcanic replenishment, and the presence or absence of magnetic shielding. Earth would not instantly become Mars, but it could become a more exposed version of itself. That is the key idea. Magnetic shielding is important, but it is not the only ingredient in habitability. A planet also needs enough gravity to hold an atmosphere, the right distance from its star to allow suitable temperatures, a chemical environment that supports stable conditions, and geological processes that recycle gases over time. Oceans matter. Volcanism matters. Plate tectonics may matter. The sun's behavior matters. Time matters most of all, because planetary change is often less like a lightning strike and more like a very patient sculptor. So the disappearance of Earth's magnetic field would not be a single catastrophe. It would be a rearrangement of risk. The world at the surface would remain familiar at first, while space-based technology and the upper atmosphere began to feel the loss more clearly. Satellites would become more vulnerable. Astronauts would require greater protection. Auroras would change. Compasses would become relics. Some animals could lose an important navigational cue. Power systems might face new stresses during solar storms, and over long stretches of time, the atmosphere would meet the sun's charged particles with one less layer of defense. The more accurate picture is quieter than the disaster version, but also more interesting. Earth would not instantly become dead. It would become less sheltered. It would still have air, oceans, gravity, weather, mountains, and life. but the invisible negotiation between planet and star would become rougher. The Sun would not need to become more dangerous. Earth would simply have lost one of the ancient systems that helped soften the meeting. The first systems to feel the loss of Earth's magnetic field would not be forests, oceans, or cities. They would be the machines already living high above most of the atmosphere, circling the planet in the thin and restless environment of near-Earth space. Satellites are often described as being above Earth, but in practical terms many of them are still part of Earth's extended environment. They orbit through regions shaped by gravity, faint traces of atmosphere, charged particles, radiation, sunlight, and magnetism. They're close enough to depend on Earth, but high enough to lose much of the protection that people on the ground take for granted. If Earth's global magnetic field disappeared, satellites would be among the first things exposed to the change. The reason is simple, but important. Earth's lower atmosphere is a thick and generous shield. It absorbs and scatters many energetic particles before they can reach the surface. A person standing at sea level is protected by kilometers of air overhead. A satellite is not. It may have shielding built into its structure, and many do, but it cannot wrap itself in an entire atmosphere. It has to survive in a place where the sun's charged particles, cosmic rays from beyond the solar system, and trapped radiation around Earth can all become practical engineering problems. Energetic particles can harm satellites in several different ways. Sometimes a charged particle passes through an electronic component and changes the state of a bit of data. This is called a single event upset. It may sound tiny because it can involve a very small electronic change, but satellites run on delicate systems where tiny errors can become rather impolite. A corrupted instruction, a confused sensor reading, or a disrupted computer process can cause glitches, resets, or temporary loss of function. Other problems are more gradual. Charged particles can build up on spacecraft surfaces, creating electrical charging that may discharge suddenly and damage sensitive components. Solar panels can degrade as radiation slowly damages the materials that convert sunlight into electricity. Detectors and cameras can suffer increased noise, meaning their measurements become fuzzier or less reliable. Instruments designed to observe Earth, the Sun, or distant space may find their data interrupted by particle hits, a little like trying to listen to gentle music while someone keeps tapping the microphone. Different satellites would face different risks depending on where they orbit. Low Earth orbit is the region where many Earth observation satellites, scientific spacecraft, and crewed stations travel. It sits above most of the atmosphere, but still close enough that faint atmospheric drag matters. Medium Earth orbit is home to navigation satellites, including the Global Positioning System. Geostationary orbit lies much farther out, where communications and weather satellites can match Earth's rotation and appear to hover over the same part of the planet. Polar orbit carries spacecraft over high latitudes, allowing them to scan the entire Earth over time, but also taking them through regions where charged particle exposure can be more intense. If the magnetic field vanished, these environments would not all become dangerous in the same way. Low Earth orbit might face increased exposure to particles that the magnetosphere would normally redirect or trap differently. Medium Earth orbit would be especially important because navigation satellites live there, and their timing signals are woven into modern life. Geostationary satellites would have to manage a harsher space weather environment over long periods. Polar orbiting satellites could face stronger particle effects, because their paths naturally pass over regions connected to Earth's magnetic poles and upper atmosphere. This matters because satellites are not just useful gadgets floating politely overhead. They are part of the hidden infrastructure of modern civilization. The Global Positioning System does far more than help people find a restaurant, although that is noble work when hunger is involved. It provides precise timing signals used by banking systems, telecommunications networks, power grids, shipping, aviation, emergency services, and scientific measurements. If navigation satellites became less reliable, the effects could spread into places that do not look space-related at all. Weather satellites would also be vulnerable. These spacecraft monitor clouds, storms, sea surface temperatures, atmospheric water vapor, wildfire smoke, hurricanes, and climate patterns. They help forecasters warn communities before dangerous weather arrives. Losing reliability in weather satellites would not make weather worse, but it could make people worse at seeing it coming. That is a serious difference. A storm is less frightening when there is time to prepare, and satellites are part of how that preparation happens. Communications satellites would face their own problems. Many provide television, internet links, military communications, maritime communication, aviation links, and emergency connectivity in remote regions. Earth observation spacecraft would risk noisier sensors and shortened lifetimes. Scientific missions studying the Sun, Earth's magnetic environment, the atmosphere or deep space would also be affected, partly because the very environment they study would become harsher to survive in. This is why organisations such as NASA, the European Space Agency, the National Oceanic and Atmospheric Administration, and the United States Space Force pay close attention to space weather and the radiation environment around Earth. NASA and the European Space Agency operate scientific missions and spacecraft that study Earth, the Sun, and near-Earth space. The National Oceanic and Atmospheric Administration monitors space weather and provides forecasts that help satellite operators, aviation planners, and power grid managers prepare for solar disturbances. The United States Space Force tracks many objects in orbit and has responsibilities linked to space operations and satellite security. Not every satellite would fail instantly if the magnetic field disappeared. That is worth making very clear. Spacecraft are already built for a hostile environment. Engineers use radiation-hardened electronics, shielding, error-correcting systems, protective operating modes, redundant components, and careful mission planning. Satellites can sometimes shut down sensitive instruments during intense solar activity, turn in safer orientations, or rely on backup systems. Space engineers, who are among the world's most patient professional warriors, have been designing for radiation risk since the early space age. But a missing magnetic field would make the odds worse. More satellites would suffer anomalies, some would need more frequent resets, some instruments would degrade faster, solar panels could lose efficiency more quickly, mission lifetimes could shorten. Insurance costs, launch planning, replacement schedules, and satellite design would all have to adapt. The environment would become less forgiving, and space hardware is already operating in a place that does not exactly hand out comfort blankets. The deeper issue is dependence. Modern life leans on satellites so quietly that their importance can be almost invisible. A ship crossing an ocean, a plane following a route, a farmer using precision agriculture, a rescue team finding someone after a disaster, a bank synchronizing transactions, a weather center tracking storms, a phone estimating location, and a scientist measuring changes in sea ice may all depend on spacecraft overhead. The loss of Earth's magnetic field would reveal how much of daily life is connected to machines moving silently above the sky. So the first victims would not be dramatic in the old-fashioned sense. There would be no collapsing mountains, no instant darkening of the oceans, no sudden end to the ground beneath your feet. Instead, the trouble would begin in circuits, sensors, timing signals, solar panels, radio links, and orbital paths. The damage would be technical, scattered, and deeply modern. Earth would still look familiar from the surface, but the invisible network above it would be living in a harsher world, without the same magnetic shelter standing between it and the charged weather of the sun. For anyone standing on Earth's surface, the atmosphere is such a faithful shield that it is easy to forget it is there. It does not look like armour. It does not clank heroically when danger arrives. It simply surrounds the planet, layer after layer, absorbing and scattering much of the radiation that comes from space before it can reach the ground. But astronauts live above most of that protection, and that makes their relationship with Earth's magnetic field far more direct. An astronaut in orbit is not outside Earth's influence. The planet's gravity still holds the spacecraft in its path, and the vehicle is still moving through near-Earth space. But the thickest part of the atmosphere lies far below. The air that protects people at sea level has become extremely thin. The spacecraft itself must become the shelter, and a spacecraft is a much thinner home than an entire sky. This is why radiation is one of the great practical concerns of human spaceflight. In orbit, astronauts are exposed to forms of radiation that people on the surface rarely need to think about. Some of it comes from the sun, some comes from beyond the solar system, some is trapped around Earth by the magnetic field itself. These are not all the same thing, and the differences matter. Solar energetic particles are bursts of high-energy particles from the sun, often associated with solar flares and coronal mass ejections. They can arrive during solar storms, when the sun releases sudden eruptions of energy and material. These events are especially important because they can increase radiation levels quickly. A calm day in orbit can become less calm if the sun decides to throw a charged particle tantrum, which it does not announce with the politeness one might prefer. Galactic cosmic rays are different. They come from outside the solar system, often from powerful events such as supernova explosions and other energetic astrophysical processes. They're extremely fast, highly energetic particles that travel through space from distant regions of the galaxy. Unlike solar energetic particles, they are not only a problem during solar storms, they are part of the background radiation environment of space, always present, difficult to shield against completely, and very good at reminding human beings that the galaxy was not designed with soft biological tissue in mind. Then there are trapped radiation belt particles. These are energetic particles held around Earth by the planet's magnetic field, especially in the Van Allen radiation belts. The belts are not evenly dangerous everywhere, and spacecraft in low Earth orbit usually remain below the most intense regions for much of the time. Still, orbital paths, altitude, inclination, and solar activity all affect exposure. Some regions, such as the South Atlantic Anomaly, allow higher radiation levels to reach lower orbital altitudes, creating an extra concern for spacecraft and crews. Earth's magnetic field helps reduce some radiation exposure in low Earth orbit by shaping and deflecting charged particles, but it's not the only protection astronauts have. Spacecraft shielding matters, mission timing matters, monitoring the sun matters, space weather forecasting matters, crew procedures matter. The International Space Station, for example, is designed with radiation protection in mind, and space agencies track solar activity so crews can take shelter in more protected areas if needed. The International Space Station has been operated through cooperation between major space agencies, including NASA, Roscosmos, the European Space Agency, the Japan Aerospace Exploration Agency, and the Canadian Space Agency. These organizations have long experience managing the risks of human life above the atmosphere. Their work includes measuring radiation exposure, setting safety limits, designing shielding, planning missions carefully, and studying how long-duration spaceflight affects the human body. Even with these protections, astronauts already receive higher radiation doses than people living on the ground. That does not mean every moment in orbit is immediately dangerous, but it does mean exposure must be tracked carefully. Radiation can damage cells and DNA, and over time it can raise health risks, including cancer risk. The concern is not usually one dramatic instant, but accumulated exposure across days, weeks, months, or repeated missions. Space is often most dangerous in this very uncinematic way, quietly, gradually, and with paperwork. If Earth's magnetic field disappeared, long-duration missions in low Earth orbit would become harder to manage. The atmosphere would still provide some shielding at lower orbital altitudes, because there are still traces of air above Earth, but the broader magnetic shelter would be gone. More charged particles from the Sun and space could reach near-Earth regions more directly. Spacecraft would need stronger shielding, better forecasting, stricter mission planning, and possibly shorter crewed stays depending on the radiation environment. The danger would be especially sharp during solar storms. A powerful solar energetic particle event can increase radiation exposure quickly, and without Earth's magnetosphere helping to redirect and shape incoming charged particles, astronauts would have less natural protection. Spacecraft would need safe areas with extra shielding, sometimes called storm shelters, where crew members could wait during dangerous periods. The idea sounds dramatic, but in practice it would be very practical. Find the thickest available protection, reduce exposure, and let the Sun finish being difficult. This issue becomes even more important when thinking about missions beyond low Earth orbit. Astronauts travelling to the Moon or Mars already leave behind much of Earth's magnetic protection. The Apollo astronauts briefly crossed through the Van Allen radiation belts and travelled beyond the magnetosphere for short missions. Future missions to the Moon, especially longer stays and journeys to Mars, would involve much longer exposure to solar storms and galactic cosmic rays. Radiation protection is therefore already a central part of planning for deep space exploration. A vanished magnetic field would make the space around Earth more like a harsher version of the environment that deep space mission planners already worry about. It would not make human spaceflight impossible, but it would make it more difficult, more costly, and more dependent on protective engineering. More mass might need to be devoted to shielding. Missions might need to be timed around solar activity more carefully. Crews might need stricter exposure limits. Space stations could require redesigns if they were expected to remain occupied for long periods. This brings the wider lesson into focus. Earth's magnetic field matters most where the atmosphere becomes thin or absent. At sea level, the air above you is doing a great deal of the protective work. In orbit, that protection is mostly gone, and the magnetic field becomes far more important. The higher a person travels from the thick lower atmosphere, the more clearly Earth's invisible shield becomes part of survival. Astronauts already live in a carefully managed compromise between danger and protection. They float above the clouds, but not beyond risk. They see Earth as a bright, curved world beneath them, beautiful and fragile, while their spacecraft quietly measures particles that human senses cannot detect. If the magnetic field disappeared, that fragile balance would shift. The view would still be breathtaking. The planet would still glow below. But the space around it would become less forgiving, and every journey above the atmosphere would need to treat the invisible weather of the Sun with even greater respect. Auroras are among the most beautiful signs that Earth is not isolated from space. They appear as curtains, ribbons, arcs, and glows of light, often moving slowly across polar skies in green, red, purple, or blue. They can look soft enough to be painted onto the night, and strange enough to feel almost unreal. But an aurora is not just a decoration placed above the world for dramatic effect, although nature does have suspiciously good lighting design. It is a physical event, created when charged particles from space interact with gases in Earth's upper atmosphere. The particles usually begin with the Sun. During ordinary solar activity, the Sun constantly releases the solar wind, a flow of charged particles moving outward through the solar system. During more energetic events, such as solar flares and coronal mass ejections, the Sun can send larger bursts of charged material into space. When some of these particles reach Earth, they encounter the planet's magnetic field. Instead of simply falling straight into the atmosphere everywhere, many are guided along magnetic field lines toward the polar regions. This is why auroras are usually concentrated near the Arctic and Antarctic. Earth's magnetic field has a shape that channels charged particles toward high latitudes, where magnetic field lines dip down into the atmosphere. The particles travel along those invisible pathways until they reach the upper layers of air. There, they collide with atoms and molecules, transferring energy to them. A moment later, those atoms and molecules release that energy as light. The main gases involved are oxygen and nitrogen. Oxygen can produce the familiar green glow that is so strongly associated with auroras. At higher altitudes, oxygen can also produce red light, which often appears softer and more diffuse. Nitrogen can contribute blue, purple, and reddish tones, especially when energetic particles interact with nitrogen molecules and ions. The exact colours depend on altitude, particle energy, atmospheric composition, and the type of collision taking place. So when an aurora ripples overhead, the sky is not simply glowing, it is the upper atmosphere briefly turning particle impacts into colour. Most auroras happen high above the surface, in regions of the atmosphere called the thermosphere and the ionosphere. The thermosphere is an upper atmospheric layer where temperatures can become very high because sparse gas absorbs energetic solar radiation, although it would not feel hot in the everyday sense because the air is extremely thin. The ionosphere overlaps with parts of the upper atmosphere where sunlight and particle impacts create charged atoms and molecules called ions. This region matters not only for auroras, but also for radio communication, satellite signals, and the way Earth responds to space weather. The ionosphere is especially important because charged particles affect how radio waves travel. Under some conditions, radio signals can be reflected, bent, disrupted, or absorbed. This means auroras are linked to communication effects as well as visual beauty. A glowing sky can be a sign that the upper atmosphere is electrically disturbed. It may look peaceful from below, but high above, particles and magnetic fields are having a rather busy evening. If Earth's magnetic field disappeared, auroras would not simply vanish. In fact, the sky might glow in stranger places. Without a strong global magnetic field guiding particles mainly toward polar regions, charged particles from the Sun could interact more directly with the upper atmosphere across wider areas. Auroral-like emissions could become less neatly arranged around the poles and more tied to where solar particles and atmospheric gases happen to meet. This would not mean every night sky would become a permanent glowing curtain. The brightness and location would still depend on solar activity, particle energy, atmospheric conditions, and how Earth's upper atmosphere responded, but the familiar geography of auroras would change. The polar regions would no longer hold the same special magnetic role. Instead of auroras being mostly a high-latitude phenomenon, more of the planet could experience particle-driven glows, especially during active solar conditions. That sounds beautiful, and it might be. A world where auroras appeared farther from the poles could be visually stunning. People in places that rarely see auroras might look up and find the sky softly flickering with colours, usually reserved for northern and southern latitudes. The sight might feel magical, as if the planet had become more generous with its wonders. But the beauty would come with a warning. A more widely glowing sky would also mean a more exposed atmosphere. Auroras are not dangerous simply because they are pretty, but they are evidence of energy entering the upper atmosphere from space. If that energy became more widespread because the magnetic field had weakened or disappeared, the glow would be a symptom of a rougher relationship between Earth and the Sun. History gives a hint of what extreme space weather can do, even with Earth's magnetic field still present. In 1859, the Carrington event became one of the most powerful geomagnetic storms ever recorded. It followed intense solar activity and produced auroras seen unusually far from the poles, including at low latitudes where such displays are rare. Telegraph systems, the high technology of the time, experienced electrical disturbances. Some operators reportedly received shocks, and some equipment continued working even when disconnected from normal power because induced currents were flowing through the lines. The Carrington event was not caused by Earth losing its magnetic field. That point is important. Earth still had its magnetic shield. The event showed something different, that a strong solar storm can disturb Earth's magnetic environment enough to push auroras far beyond their usual homes. It was a glimpse of how powerful the sun can be when it throws a major disturbance toward Earth. If the magnetic field were absent, the planet's interaction with such solar activity would be very different and likely harsher for the upper atmosphere and technology. Auroras, therefore, sit at the meeting point between beauty and exposure. They are lovely because the atmosphere glows. They are scientifically important because the glow reveals a transfer of energy from space into the upper air. They remind us that Earth is not sealed away from the solar system. The planet is constantly interacting with the sun's particles, fields, and storms. In ordinary times, the magnetic field gives this interaction structure. It channels particles, shapes the auroral ovals, protects much of the planet from direct particle bombardment, and helps keep the most dramatic displays near the poles. It turns a potentially messy collision between star and planet into a patterned event. The sky glows most strongly where the magnetic field guides the particles downward. Without that field, the pattern would loosen. The polar glow might become a wider, stranger atmospheric response. The upper sky could become more active in places that rarely see such light. The ionosphere could become more disturbed. Radio effects could become more widespread. Satellites passing above glowing regions might face harsher particle conditions. The display would still be beautiful, but it would no longer be quite so reassuring. So if Earth's magnetic field disappeared, one of the most visible changes might be written across the night sky. The planet might answer the sun with broader, stranger light. Curtains of colour could drift over unfamiliar horizons. Green and red glows might appear where they once seemed rare. The sky might become more theatrical, more alive, and more unsettling. Auroras would still be what they have always been. Atoms and molecules in the upper atmosphere releasing light after being struck by charged particles. But their meaning would shift. Instead of showing how Earth's magnetic field guides energy safely toward the poles, they might reveal how much more directly the upper atmosphere was being touched by the sun. The glow would be beautiful, yes, but it would also be a signal that the invisible shield had weakened and that Earth was meeting space with less protection than before. Space weather sounds as if it belongs high above Earth, somewhere between satellites, auroras, and the invisible edge of the atmosphere. The name itself feels distant, almost gentle, like a forecast for a place no one is likely to visit after dinner. But space weather does not always stay politely in space. Under the right conditions, activity from the sun can reach all the way down into the systems that keep modern civilization running. One of the most important ways this happens is through geomagnetic storms. A geomagnetic storm occurs when Earth's magnetic environment is strongly disturbed, usually after the sun releases a powerful burst of charged particles and magnetic field into space. When that disturbance reaches Earth, it can shake the magnetosphere, brighten auroras, disturb radio signals, affect satellites, and create electrical effects at the surface. It is a reminder that the planet's magnetic field is not just a distant shield. It is connected to the wires, transformers, pipelines, and communication systems that quietly support ordinary life. The key idea is Electromagnetic induction. When magnetic fields change, they can produce electric currents in conducting materials. This is not a rare or exotic principle. It is part of the same broad physics used in generators, transformers, and many electrical technologies. During a geomagnetic storm, changes in Earth's magnetic field can induce slow-moving electric currents through long conductors on the ground. These are called geomagnetically induced currents. Long conductors are especially vulnerable because they give these currents large pathways to travel through. Power lines can act as enormous unintended receivers. Pipelines, railway systems, and undersea cables can also be affected. A small electrical effect spread across a short object may not matter much, but across hundreds or thousands of kilometers of connected infrastructure, the same kind of disturbance can become significant. It is one of those situations where being very long and very connected is useful on a normal day and less charming when the sun is misbehaving. Power grids are a particular concern because they depend on high-voltage transmission lines and large transformers. Transformers are designed to manage alternating current under normal operating conditions. Geomagnetically induced currents are different. They can push transformers towards saturation, cause heating, distort electrical waveforms, and increase the risk of protective equipment tripping offline. In severe cases, equipment can be damaged. The problem is not that the sun plugs directly into the grid like an impatient electrician. It is that a disturbed magnetic environment can create unwanted currents through the grid itself. A major modern example happened in Quebec in 1989. A powerful geomagnetic storm disturbed the electrical grid, and within a short time the Hydro-Quebec power system suffered a major blackout. Millions of people lost electricity. The event showed that space weather was not just a scientific curiosity or a beautiful aurora maker. It could affect infrastructure on the ground in a serious and practical way. The disturbance began with solar activity far from Earth, travelled through space, interacted with the magnetosphere, and ended with lights going out in homes and cities. That chain of cause and effect is almost unsettling in its elegance. A storm on the sun, a disturbance in Earth's magnetic field, a current in a power line, a transformer under stress, and suddenly a human system built on the ground is responding to something that began 150 million kilometers away. It is hard to imagine a clearer example of modern civilization being connected to the behavior of a star. The National Oceanic and Atmospheric Administration Space Weather Prediction Center monitors solar activity and issues space weather forecasts to help reduce these risks. Its work includes tracking solar flares, coronal mass ejections, solar wind conditions, geomagnetic storms, and radiation events. These forecasts can help satellite operators, aviation planners, power grid managers, and communication systems prepare for disturbances. Space weather forecasting is not perfect, because the sun and magnetosphere are complex, but warning time can still be valuable. Even a limited forecast may allow operators to adjust grid conditions, delay sensitive operations, protect satellites, or prepare for communication disruptions. If Earth's global magnetic field disappeared, the way space weather interacted with the planet would change. The familiar magnetosphere would no longer shape incoming charged particles in the same way. Auroras would no longer be organized around the poles in the usual pattern. Satellites would face harsher conditions, and the electrical systems on and near the ground could experience a different pattern of disturbance from solar activity and upper atmospheric currents. It is important, though, not to turn this into one simple global outcome. Power grid vulnerability depends on many details. Latitude matters, because high-latitude regions are often more exposed to geomagnetic activity under present conditions. Grid design matters, because some networks are more robust, more connected, or more vulnerable than others. Local geology matters because the electrical conductivity of the ground affects how induced currents flow. Transformer design matters. Protective systems matter. Warning time matters. The choices made by grid operators during a storm matter too. A geomagnetic disturbance is not a magic switch that turns all power off everywhere. In a world without a magnetic field, engineers would have to rethink many of these protections. Power systems might need more monitoring, stronger transformer protection, improved grounding strategies, better operational planning, and more resilience against unusual currents. Pipelines could need more careful corrosion monitoring, because stray electrical currents can affect the electrochemical processes that protect metal infrastructure. Railway signalling and undersea cables could need extra safeguards. The danger would not be constant disaster, but increased vulnerability whenever solar activity became intense. This is where the invisible shield becomes surprisingly practical. It is easy to admire auroras as beautiful lights and satellites as distant machines, but the same space weather that paints the sky can also enter the nervous system of civilization. Electricity grids, navigation signals, communications, aviation routes, financial timing systems, and emergency services all depend on a stable technological environment. When Earth's magnetic surroundings are disturbed, the effects can move from the upper atmosphere into the very ordinary world of switches, signals, cables, and transformers. A vanished magnetic field would not mean every city immediately went dark. It would mean the protective arrangement between Earth and the Sun had changed. The surface would still have the atmosphere, and many systems could be redesigned or hardened over time. But modern technology would be living under a more restless sky. Space weather would become harder to ignore, because it would no longer be something that mostly concerned satellites, astronauts, and people lucky enough to see auroras. The deeper lesson is that Earth's magnetic field helps keep the Sun at a manageable distance, not in terms of kilometers, but in terms of consequences. The Sun can still disturb the planet even now, with the magnetic field in place. Without it, the boundary between solar activity and human infrastructure could become thinner and more unpredictable. So space weather is not just a sky phenomenon. It is not only a shimmer over polar snow or a problem for machines in orbit. It is part of the environment in which modern civilization exists. The wires on the ground, the satellites above, and the auroras in the night are all connected by the same invisible physics. And if Earth's magnetic field disappeared, that connection would become harder, sharper, and much more difficult to sleep through. For most of human history, finding direction was not a small convenience. It was survival, trade, exploration, migration, and the difference between getting home and becoming a cautionary tale told beside a fire. Long before satellite navigation, people used the sun, the stars, coastlines, winds, currents, landmarks, maps, memory, and eventually the magnetic compass. A compass feels beautifully simple. A needle turns, settles, and points the way. But what it is really doing is not pointing to the top of the world. It is aligning itself with Earth's magnetic field. A compass needle is magnetized. Because it is free to rotate, it lines up with the local direction of Earth's magnetic field. This means it does not point directly to the geographic North Pole, the fixed point where Earth's rotation axis meets the surface in the Arctic. Instead, it points toward magnetic north, which is related to the shape of Earth's magnetic field. Those two norths are not the same place. They are often treated as if they are identical in casual conversation, because saying northish, depending on the invisible core-generated magnetic field beneath your feet, would make hiking instructions slightly exhausting. But scientifically, the difference matters. geographic north is tied to Earth's rotation. It is the direction toward the northern end of the planet's spin axis. Magnetic north is tied to Earth's magnetic field, which is generated by motion in the liquid outer core. Because that deep motion changes over time, magnetic north moves. It does not sit politely in one permanent location. It drifts across the Arctic, sometimes slowly, sometimes more rapidly, as the magnetic field changes shape and strength. This is why navigators, surveyors, map makers, and engineers must account for magnetic declination, the angle between magnetic north and true geographic north at a particular location. To keep track of this changing field, scientists use models. One of the most important is the World Magnetic Model, maintained by organisations including the United States National Centres for Environmental Information and the British Geological Survey. The World Magnetic Model helps describe Earth's large-scale magnetic field and is used in navigation systems, aviation, mapping, smartphones, military systems, and many other tools that need magnetic direction. It is updated because the field changes. A magnetic map of Earth is not something that can be made once and then left alone forever, like an old family recipe, although even those tend to cause arguments. If Earth's magnetic field disappeared, a traditional compass would lose its purpose. The needle would no longer have a global planetary field to follow. Local magnetic objects might still affect it. Nearby metal, electric currents, or small magnetic fields could make it twitch or settle in odd directions. But it would no longer provide a reliable guide to north. It would become a delicate little pointer looking for an instruction that the planet was no longer giving. For everyday life in many places, this might not feel catastrophic at first. Most people do not navigate their morning by compass anymore. Phones, cars, aircraft, ships, and mapping systems rely heavily on satellite positioning, digital maps, inertial sensors, radio systems, visual references, and computer networks. The average person trying to find a cafe would probably worry more about battery percentage than magnetic declination. But for exploration, surveying, aviation backups, maritime navigation, military operations, field science, wilderness travel, mining, drilling, and emergency situations, the loss would still matter. A compass is old technology, but old technology is often useful precisely because it is simple, portable, and does not need a satellite constellation to be in a good mood. Modern navigation would lean more heavily on other methods. Satellite positioning systems could provide location and timing using signals from spacecraft in orbit. Inertial navigation systems could estimate position by measuring motion and acceleration, especially in aircraft, submarines, spacecraft, and military vehicles. Radio navigation could help in certain regions. Maps, landmarks, coastlines, road networks, and astronomical navigation could all still play roles. The stars would still rise and set. The sun would still cast shadows. The moon would still wander through the sky with its usual quiet confidence. But there is a sharp irony here. If Earth's magnetic field disappeared, the same event that made compasses useless could also make satellite navigation less reliable. Global Positioning System satellites and other navigation spacecraft operate above much of the atmosphere's protection. Without the magnetic field, they would face a harsher radiation environment with more risk of electronic faults, signal disruption, and shortened mission lifetimes. So humanity might lose its simplest direction-finding tool while placing even more pressure on a space-based system that had become more vulnerable at the same time. It is a little like losing an umbrella during a storm and deciding to rely entirely on a second umbrella, currently being attacked by charged particles. This would not mean navigation would collapse everywhere. Human beings are very good at building backups, especially after discovering that the first system can fail in a deeply inconvenient way. Aircraft and ships already use layered navigation methods. Surveyors combine satellite data with ground measurements. Submarines can use inertial guidance. Astronomical navigation remains possible in principle wherever the sky can be observed. But losing the magnetic field would remove one of the oldest, simplest, and most globally available reference systems humans have ever used. It would also reveal that direction is not only a human concern. Many animals appear to use Earth's magnetic field as part of their own navigation. Migratory birds, sea turtles, salmon, lobsters, bees, bats, and even some bacteria have been studied for magnetic sensing, known as magnetoreception. For them, the magnetic field is not a needle in a case. It is information woven into the environment itself. It may help with orientation, long-distance migration, returning to breeding grounds, or building a map of where they are. So a planet without magnetic north would not only confuse compasses, it would remove a quiet directional cue shared by machines, explorers, and living creatures. Geographic north would remain. The planet would still spin. The Arctic would still exist. Maps would still have tops and edges and arguments about folding, but the magnetic sense of direction would be gone. Earth would no longer whisper north through a needle, a sensor, or the hidden biology of a migrating animal. One of the planet's oldest invisible guide systems would fall silent. For humans, Earth's magnetic field is usually something measured by instruments, followed by compasses, or discussed when satellites have a difficult day. But for many other living things, magnetism may be part of the world in a far more direct way. Not visible exactly, not heard or smelled in the ordinary sense, more like a hidden direction woven into the background of life. This ability is called magnetoreception. It means the capacity of an organism to detect magnetic fields and use that information for orientation, navigation, or positioning. To human imagination, this can sound almost supernatural, but it is not magic. It is biology responding to physics. The same planet-wide field that can move a compass needle may also provide information to animals crossing oceans, flying between continents, returning to rivers, or moving through muddy water where landmarks are not especially helpful, and asking for directions is, sadly, not an option for a lobster. Magnetoreception has been linked to many different organisms. Migratory birds appear to use Earth's magnetic field as one part of their navigation system during long seasonal journeys. Sea turtles can travel enormous distances across the ocean and later return to particular nesting regions, using magnetic information as part of a wider map. Salmon are thought to use magnetic cues in the ocean before returning to the rivers where they hatched. Spiny lobsters have shown evidence of magnetic orientation. Bats, bees, and some insects also appear to respond to magnetic information in different ways. Even certain bacteria interact with magnetic fields in a remarkably direct and elegant manner. Among the clearest examples are magnetotactic bacteria. These are microscopic organisms that contain tiny magnetic particles inside their cells. These particles are arranged in structures called magnetosomes. The magnetosomes help the bacteria align with magnetic field lines, which can guide their movement in aquatic environments such as sediments, ponds, marshes, and marine habitats. For such small organisms, this is not a grand migration across a continent. It is more like having a microscopic compass built into the body, helping them move toward chemical conditions that suit their survival. Tiny life, tiny compass, still somehow more organized than many people packing for a weekend away. In larger animals, the story becomes more complex. Sea turtles offer one of the most fascinating examples. Researchers Kenneth Lohman and Catherine Lohman have carried out influential work on how young sea turtles respond to geomagnetic information. their research has helped show that turtles can use aspects of Earth's magnetic field as navigational cues during long ocean migrations. The magnetic field varies across Earth's surface in ways that can provide location information. Two important features are magnetic inclination, which describes the angle at which magnetic field lines meet Earth's surface, and magnetic intensity, which describes the field's strength. Together, these features may help animals build a kind of magnetic map. For a young sea turtle entering the ocean, this matters enormously. The sea is wide, moving, and visually repetitive. There are no road signs drifting helpfully above the waves. Currents shift, storms pass. The horizon looks very much like the horizon. Yet some turtles travel across vast ocean basins and later return to nesting areas with extraordinary precision. Magnetic information is not their only guide, but it may be one of the quiet tools that helps make such journeys possible. Migratory birds provide another rich area of study. Many birds use the sun, stars, polarized light, smell, landmarks, wind patterns, and learned routes. But experiments have also shown that magnetic fields can influence their orientation. Some birds seem able to detect the direction or inclination of Earth's magnetic field, helping them maintain a course during migration. For a small bird crossing sea, desert, or unfamiliar land, even a subtle internal sense of direction could be the difference between arriving and wandering far off route. The exact mechanisms behind magnetoreception are still debated. In some animals, scientists have investigated the possibility of magnetite-based sensing. Magnetite is a naturally magnetic mineral, and tiny particles of it have been found in some biological tissues. The idea is that such particles might respond physically to magnetic fields, providing a signal the nervous system can detect. This would be somewhat like having a compass needle built into living tissue, though the actual biology is far subtler than a tiny needle wobbling politely inside the head. Another major idea involves cryptochrome proteins. Cryptochromes are light-sensitive proteins found in plants and animals, including the eyes of some birds. Some researchers have proposed that cryptochromes could allow animals to detect magnetic fields through quantum chemical reactions affected by magnetism. This is sometimes called a radical pair mechanism. The details are still an active area of research, and scientists continue to investigate how these proteins might contribute to magnetic sensing. It is one of those places where biology, chemistry, and physics meet so closely that the boundaries between them begin to feel more like suggestions. It is important not to oversimplify this. Animals do not all use magnetic fields in the same way. Some may use them as a compass, helping determine direction. Others may use them as part of a map, helping estimate location. Some may rely on magnetic cues only during certain life stages or certain journeys. Others may use magnetism alongside many other signals, switching between them depending on conditions. Nature rarely builds one-tool systems when a messy, layered, slightly confusing backup plan will do. So if Earth's magnetic field disappeared, animal migration would not simply stop everywhere at once. Birds would not all fall from the sky in baffled spirals. Sea turtles would not immediately forget what an ocean is. Many animals use multiple cues: stars, sunlight, smells, currents, coastlines, wind, temperature, sound, landmarks, memory, and social learning. Some species might adapt by leaning more heavily on these other systems. Others might already use magnetism only as one helpful layer among many. But the disappearance of the magnetic field could still be deeply disruptive. Species that rely heavily on magnetic information during long-distance migration might lose an important part of their orientation system. Young animals making their first journeys could be especially vulnerable if they depend on an inherited magnetic maps rather than learned routes. Sea turtles crossing ocean basins, birds migrating at night, salmon navigating through changing marine environments, and lobsters moving across the seafloor could all face new uncertainty. The effects would likely vary widely. Some populations might cope well, others might experience poorer navigation, longer journeys, greater energy costs, lower survival, or reduced breeding success. Small changes in navigation can have large ecological consequences if they affect when animals arrive, where they feed, or whether they reach nesting and spawning grounds. Migration is already difficult. Removing a planetary cue would make it harder for some species, even if it did not make it impossible. This reveals another side of Earth's magnetic field. It is not only a shield for satellites or a guide for compasses. It is part of the sensory world of life. To some organisms, magnetism may be as real and useful as light, scent, or sound. Humans mostly notice the field when instruments translate it for them, but other creatures may carry pieces of that invisible planet inside their behavior. A world without Earth's magnetic field would therefore be quieter in a strange way. Not visually quiet and not silent in the air, but missing a hidden signal that many forms of life have learned to use. The planet would still have winds, stars, tides, currents, coastlines, and sunlight. But one of its deepest directional whispers would be gone, and many travellers of the living world would have to find their way without it. Radiation is one of those words that can make a peaceful topic feel suddenly less peaceful. It sounds invisible, serious, and faintly like something that should be handled by people in heavy suits who know exactly which buttons not to press. But radiation is not one single thing. It comes in different forms, with different energies, different sources, and very different effects. To understand what would happen at Earth's surface without the magnetic field, it helps to separate the dramatic fear from the actual physics. People on the ground are protected from space radiation by two main shields, the atmosphere and Earth's magnetic field. These two protections work in different ways. The magnetic field helps redirect many charged particles before they can enter the upper atmosphere directly. The atmosphere then acts as a thick physical blanket of gas, absorbing, scattering, and slowing many particles and forms of radiation before they can reach the surface. One shield works through magnetism, the other works through matter. At sea level, the atmosphere is especially important. Above your head is a column of air extending upward for many kilometers. It may feel weightless because you're used to it, but it is substantial. Incoming particles from space must pass through nitrogen, oxygen, argon, water vapor, carbon dioxide, and other trace gases before reaching the ground. Along the way, many are blocked or transformed. High-energy particles may strike atoms in the atmosphere and create showers of secondary particles, but most of the original energy is absorbed long before it reaches people, animals, plants, and the cup of tea that did not ask to become part of a cosmic radiation discussion. This is why radiation exposure at Earth's surface is far lower than in space. An astronaut in orbit lives above most of the atmosphere, with only a spacecraft hull and mission shielding between the body and the surrounding particle environment. A person on the ground lives beneath a deep atmospheric ocean. The sky is not empty overhead. It is protective mass, spread gently above the world. The magnetic field adds another layer, especially against charged particles. Charged particles are particles with electric charge, such as protons and electrons. Because they are charged, their paths can be bent by magnetic fields. Earth's magnetic field helps guide, deflect, or trap many of these particles before they reach lower atmospheric layers. This is part of why the radiation environment is different at different latitudes and altitudes. The field is not a perfect shield, but it helps shape where particles go and how strongly they affect the upper atmosphere. If the magnetic field disappeared, the surface would not instantly become deadly. That point matters. The atmosphere would still be there, still thick, still doing a large part of the shielding. People would not step outside and suddenly find themselves in the same radiation environment as an astronaut. The lower atmosphere would continue to reduce exposure dramatically. But the radiation environment would change. The increase would be most noticeable where the atmosphere is thinner or where Earth's magnetic protection matters more strongly. High altitudes would be more exposed than sea level. Mountain regions would generally receive more cosmic radiation than low coastal areas because there is less air overhead. Aircraft would be more exposed still because cruising altitude places passengers and crew above much of the densest atmosphere. Near polar regions, radiation exposure is already influenced by the shape of Earth's magnetic field, and without a global field, the pattern of exposure would likely become broader and less neatly organized. Aviation is a useful example because it already sits between the protected surface and the harsher environment of space. Airline crews and frequent flyers receive slightly higher doses of cosmic radiation than people who spend most of their time at ground level. The doses are still generally low and monitored within the context of occupational health, but the difference is real. At cruising altitudes, there is simply less atmosphere above the aircraft to absorb incoming particles. Flying does not turn someone into an astronaut, but it does move them a small step closer to the radiation environment that astronauts worry about. During major solar energetic particle events, the risk could increase more sharply. These events happen when the Sun releases bursts of high-energy particles, often associated with solar flares or coronal mass ejections. With a magnetic field, Earth has some help redirecting and organizing incoming charged particles. Without it, more of that particle energy could interact with the atmosphere more directly. The surface would still be shielded by air, but high-altitude flights, polar routes, astronauts, satellites, and upper atmospheric chemistry would become more vulnerable. It also helps to distinguish ionizing radiation from ordinary visible light. Visible light is radiation too, in the broad sense, because it is electromagnetic energy. But visible light is not usually energetic enough to knock electrons out of atoms or molecules. Ionizing radiation is different. It has enough energy to ionize atoms, meaning it can remove electrons and alter chemical bonds. This matters for living tissue because damage to molecules, including DNA, can increase health risks if exposure is high enough or repeated over time. Particle radiation from space can be ionizing, which is why it is treated carefully in aviation, spaceflight, medicine, and radiation protection. Bodies such as the International Commission on Radiological Protection and the World Health Organization are connected to radiation protection, health guidance, and risk assessment. Their work helps shape how societies think about exposure, safety limits, occupational risk, and public health. Radiation risk is not judged by panic, but by dose, energy, duration, biological effect, and probability. This is not quite as emotionally satisfying as shouting danger at the sky, but it is much more useful. The disappearance of Earth's magnetic field would therefore weaken one layer of the planet's radiation defense. It would not remove every protection. It would not make the surface instantly uninhabitable. It would not mean ordinary sunlight had suddenly become the same as high-energy particle radiation, but it would make Earth more exposed to charged particles from the Sun and space, especially in the upper atmosphere and at high altitude. For most people at sea level, the early change might be less obvious than expected. The air would still stand guard. Buildings, soil, water, and distance from the upper atmosphere would still matter. But the protective system around Earth would be poorer than before. Flights might require more careful monitoring. High-altitude regions could see increased exposure. Solar storms would become more concerning. Space agencies, aviation authorities, and radiation protection experts would pay closer attention to conditions that had once been softened by the magnetic field. So the surface would remain sheltered, but not quite as sheltered. That is the most accurate picture. Earth would still have its atmosphere, the great quiet filter above every landscape. But one of the planet's invisible outer defences would be gone. The world below would continue, familiar and breathable, while the boundary between life and space became a little thinner than it used to be. Above the familiar weather of clouds, rain, wind and blue sky, Earth's atmosphere becomes thinner, stranger, and more electrically active. It is easy to imagine the atmosphere as one simple blanket, but it is really a layered structure, with each region behaving in its own way. The lower atmosphere is where most weather happens. Higher up, the air becomes sparse, the chemistry changes, and sunlight and charged particles can have effects that would seem very distant from ordinary life on the ground. If Earth's global magnetic field disappeared, the upper atmosphere would become more directly exposed to charged particles from the sun and from space. The magnetic field normally helps redirect many of these particles, guiding some toward polar regions and keeping others from plunging directly into the atmosphere across wider areas. Without that magnetic organization, more particle energy could reach upper atmospheric layers in less controlled patterns. The result would not be a single simple effect, but a series of chemical, electrical and thermal changes that would depend on solar activity, altitude, and time. One of the most important atmospheric regions for life is the stratosphere. This layer sits above the lower weather-filled troposphere and contains the ozone layer. Ozone is a form of oxygen made of 3 oxygen atoms joined together. It is only a trace gas, but it has an enormous role. The ozone layer absorbs much of the sun's harmful ultraviolet radiation before it reaches the surface. Without this protection, more damaging ultraviolet light would reach living tissue, increasing risks to skin, eyes, plants, plankton, and ecosystems. Ultraviolet radiation is not the same thing as charged particle radiation. This distinction matters because the word radiation gets used for many different phenomena. Visible light is radiation. Heat from a warm fire is radiation. Ultraviolet light from the sun is radiation. Energetic particles from space are also often discussed as radiation. But these are not identical. Ultraviolet radiation is electromagnetic energy, like visible light but with shorter wavelengths and higher energy. Charged particle radiation involves particles such as protons and electrons moving at high speeds. Atmospheric chemistry is something else again. It is the chain of reactions between atoms, molecules, ions, and sunlight in the air. These categories can interact, but they should not be blurred together. A solar storm does not damage ozone in the same way that industrial chemicals damaged the ozone layer during the 20th century. Charged particles entering the upper atmosphere can change chemistry by breaking molecules apart and creating reactive compounds. Under certain conditions, solar energetic particles can produce nitrogen oxides in the atmosphere. Nitrogen oxides can participate in reactions that reduce ozone, especially in polar or upper atmospheric regions. But the details depend heavily on altitude, season, particle energy, atmospheric circulation, and the chemistry already present. This is different from the well-known ozone depletion caused by human-made chemicals such as chlorofluorocarbons. Those chemicals were once widely used in refrigeration, aerosol sprays, and industrial processes. When they reached the stratosphere, they could release chlorine and bromine atoms that destroyed ozone through catalytic reactions. The discovery of severe Antarctic ozone depletion helped lead to the Montreal Protocol, an international agreement adopted in 1987 to phase out many ozone-depleting substances. The Montreal Protocol is often considered one of the most successful environmental agreements in history because it helped place the ozone layer on a path toward recovery. That story is important here because it shows 2 things at once. First, the ozone layer is delicate enough that chemistry can seriously affect it. Second, Not all ozone problems have the same cause. Chemical ozone depletion from chlorofluorocarbons is not the same as particle-driven atmospheric chemistry from solar energetic particles. Both can involve ozone loss, but the pathways, sources, timescales, and solutions are different. Treating them as one vague radiation problem would be scientifically untidy, and the atmosphere deserves better housekeeping than that. In a world without Earth's magnetic field, the upper atmosphere would likely face more direct particle impacts, especially during active solar periods. Energetic particles could increase ionization, change the balance of nitrogen oxides and hydrogen oxides, affect ozone chemistry, heat parts of the upper atmosphere, and disturb the ionosphere. The ionosphere is the region where solar radiation and particle impacts create charged atoms and molecules, and it matters for radio communication and satellite signals. A more exposed ionosphere could mean more variable communication conditions and more complicated effects on navigation signals. The thermosphere would also be important. This is a very high layer of the atmosphere where incoming energy from the sun can heat sparse gases. During strong solar activity, the thermosphere can expand, increasing drag on satellites in low Earth orbit. Even now, solar storms can cause the upper atmosphere to swell slightly, affecting spacecraft paths. Without the usual magnetic shielding, changes in heating and particle input could become more pronounced or differently distributed. The result would be another reminder that the atmosphere does not end abruptly. It thins gradually into space, and the boundary between air and orbit is more active than it looks from below. The effects would not be uniform across the whole planet. They would vary with the sun's behaviour. During quiet solar conditions, changes might be more modest. During powerful solar energetic particle events, the upper atmosphere could experience stronger chemical disruption. Altitude would matter, because different reactions dominate in different layers. Time would matter, because some chemical changes might fade quickly, while others could influence atmospheric composition for longer periods. Atmospheric circulation would matter too, because gases created in one region can be transported elsewhere. The surface would still be protected by the bulk of the atmosphere, but the chemistry above it would be under greater stress. This is one reason the magnetic field matters beyond satellites and astronauts. It helps shape the flow of charged particles into the upper atmosphere, and that upper atmosphere helps regulate the environment below. The connection is indirect, but very real. A disturbance high above the clouds can influence radio signals, satellite drag, radiation exposure at altitude, and the chemistry that affects how much ultraviolet light reaches the ground. So the disappearance of Earth's magnetic field would not simply remove a shield in space. It would change how energy from the sun enters the upper layers of air. The ozone layer would not vanish overnight. The sky would not suddenly become poisonous. But one more part of Earth's protective system would be weakened, and the delicate chemistry above the weather would have to absorb more of the sun's charged particle behaviour. Earth's atmosphere is not just a passive blanket. It is a working chemical system, constantly shaped by sunlight, particles, motion, temperature, and time. The magnetic field helps keep that system from being disturbed too directly by the restless sun. Without it, the upper atmosphere would still protect the surface, but it would do so with less help from the invisible shield above it. If Earth's magnetic field disappeared, one of the biggest questions is also one of the easiest to misunderstand. Would the atmosphere be stripped away into space? The calm answer is no, not immediately. The atmosphere would not vanish in a day. The sky would not suddenly thin into nothing. Clouds would not flee upward in a dramatic atmospheric evacuation, which would be visually impressive but scientifically rude. Earth's air is held mainly by gravity, and that gravity would still be there. The planet would still be massive enough to hold nitrogen, oxygen, water vapour, carbon dioxide, argon, and the many trace gases that make up the atmosphere. But the longer answer is more interesting. Without a magnetic field, Earth's upper atmosphere could become more vulnerable to loss over very long timescales. Not hours, not days, not the kind of timescale where someone looks out of the window after lunch and notices slightly less sky. Atmospheric loss is usually a slow planetary process, shaped by the sun, gravity, chemistry, temperature, geology, and time. The magnetic field matters because it helps reduce some direct interactions between the solar wind and the upper atmosphere. Remove that shield, and the planet becomes more exposed. Atmospheric escape is the process by which atoms and molecules leave a planet and are lost to space. Every planet with an atmosphere experiences some kind of atmospheric escape. Even Earth loses tiny amounts of gas all the time. Hydrogen and helium, being very light, are especially good at slipping away. This does not mean the atmosphere is rapidly draining like air from a punctured balloon. It means that the upper edge of an atmosphere is never perfectly sealed. It is a boundary where particles can sometimes gain enough energy to leave forever. There are several ways atmospheric escape can happen. Jeans escape is one of the simplest to picture. In the very upper atmosphere, some light particles move fast enough to overcome a planet's gravity and drift away into space. This is most important for light gases, especially hydrogen. Temperature matters, because hotter particles move faster. Gravity matters too, because a larger planet holds onto gases more strongly. Earth's gravity is strong enough that heavy gases such as nitrogen and oxygen do not easily escape this way, but light gases can still gradually leak away from the upper atmosphere. Other forms of escape are more energetic. Non-thermal escape describes processes where particles are removed not simply because of heat, but because they are kicked, accelerated, or chemically produced with enough energy to leave. Sputtering happens when energetic particles from the solar wind or magnetosphere strike the upper atmosphere and knock atmospheric particles away, a little like tiny cosmic billiard balls colliding at very high speed. Ion pickup happens when neutral atoms in the upper atmosphere become ionized, meaning they gain an electric charge and are then swept away by electric and magnetic fields carried by the solar wind. There is also polar wind, a process in which charged particles flow outward along magnetic field lines from polar regions. This may sound odd, because the magnetic field protects the planet in many ways, yet it can also provide pathways through which some particles escape. The point is not that magnetic fields are simply good or bad. Planetary atmospheres are messy systems. A magnetic field can reduce some escape processes while shaping or allowing others. Nature, as usual, refuses to behave like a tidy diagram. Mars is the planet most often brought into this conversation, and for good reason. Mars appears to have lost its global magnetic field early in its history. Today it has only patches of crustal magnetism, remnants of ancient magnetic fields locked into rocks. Mars also has a very thin atmosphere compared with Earth's. Its surface pressure is less than 1% of Earth's sea level pressure, and its atmosphere is mostly carbon dioxide. Evidence from orbiters, landers, and rovers shows that ancient Mars once had liquid water on its surface, including river valleys, lake beds, deltas, and minerals formed in water. This makes Mars a powerful warning, but it must be used carefully. Mars did not become the planet it is today, only because it lost its magnetic field. Mars is smaller than Earth, with much lower gravity. That makes it easier for gases to escape. Its interior cooled more quickly, reducing long-term volcanic activity and weakening the geological recycling of atmospheric gases. It is farther from the Sun, colder, and has a different atmospheric and climate history. Losing its global magnetic field likely made Mars more vulnerable to the solar wind, but it was one part of a much larger transformation. NASA's MAVEN mission, whose name stands for Mars' atmosphere and volatile evolution, has been especially important for studying how the solar wind interacts with the Martian atmosphere today. MAVEN measures atmospheric escape and helps scientists understand how Mars has lost gas to space over time. Its observations show that solar activity can increase atmospheric loss, especially during solar storms. Mars gives scientists a real planetary laboratory for studying what happens when a world with little global magnetic protection meets the solar wind more directly. Then there is Venus, which complicates the story in the opposite direction. Venus does not have an Earth-like global magnetic field generated by an internal dynamo. Yet it has a massive atmosphere, far thicker than Earth's, dominated by carbon dioxide. The pressure at the surface of Venus is crushing, roughly comparable to being deep underwater on Earth. Venus shows very clearly that a strong internal magnetic field is not the only thing that determines whether a planet keeps an atmosphere. Venus has strong gravity, a thick atmosphere, and an induced magnetosphere created by the interaction between the solar wind and its upper atmosphere. It has lost water over time, and its atmosphere has evolved under extreme greenhouse conditions, but it has not been stripped bare. This matters because it prevents the oversimplified claim that no magnetic field automatically means no atmosphere. Planetary survival depends on many interacting conditions. Earth has several advantages of its own. It has stronger gravity than Mars. It has active geology, including volcanism and long-term cycling of gases. It has oceans, which store heat and carbon and influence atmospheric chemistry. It sits at a distance from the sun where liquid water can remain stable on the surface. Its atmosphere is thick enough to provide strong shielding at the ground, and its magnetic field helps reduce some direct exposure of the upper atmosphere to charged particles. Habitability is not one switch. It is a system of overlapping protections. So if Earth's magnetic field vanished, the atmosphere would not be ripped away in one dramatic scene. Instead, the upper atmosphere would become more exposed to the solar wind. Some escape processes could become more important. Over very long timescales, especially during periods of strong solar activity, Earth might lose atmospheric particles more easily than it does now. The change would be real, but slow and complicated. That is the most scientifically honest picture. Earth would not instantly become Mars. It would not copy Venus either. It would become Earth with one major layer of protection removed. The planet's gravity, oceans, chemistry, geology, and atmosphere would still matter. The magnetic field is important, but it is not a magic shield that single-handedly holds the sky in place. It is one member of a larger planetary team, quietly helping Earth remain the breathable, blue, strangely fortunate world it is. Mars is the planet that most often enters the conversation when people ask what would happen to Earth without a magnetic field. It is close enough to study in detail, alien enough to show a different planetary path, and familiar enough that its rusty deserts have become part of the human imagination. Mars looks quiet now, cold, dry, and thin-aired, but the evidence preserved across its surface tells a more complicated story. Today, Mars does not have a strong global magnetic field like Earth's present-day dipole field. Earth's field surrounds the whole planet and stretches outward into a magnetosphere. Mars has something different. It has patches of crustal magnetism, regions where ancient rocks still hold traces of magnetic fields from long ago. These magnetized crustal areas suggest that early Mars once had an internal dynamo, a process in its core capable of generating a global magnetic field. But that dynamo shut down billions of years ago. The result is a planet that now meets the solar wind in a much more exposed way than Earth does. Mars still has interactions between its atmosphere and the Sun, but it does not have the same broad magnetic shield generated from deep inside. Its upper atmosphere is more directly vulnerable to charged particles streaming from the Sun, and over immense spans of time, that exposure has contributed to atmospheric loss. But Mars must be handled carefully. It is tempting to say that Mars lost its magnetic field, then lost its atmosphere, then lost its water, and that is the entire story. That version is simple, memorable, and not quite honest. Planetary history is rarely a neat row of dominoes. Mars became the world it is today through many linked changes: loss of internal heat, weakening volcanic activity, atmospheric escape, lower gravity, changing climate, impact history, solar activity, and the disappearance of stable surface water. The magnetic field was important, but it was not the only character in the drama. Ancient Mars shows strong evidence for liquid water. Orbiters have photographed branching valley networks that look like they were carved by flowing water. Some landscapes preserve ancient river channels, lake beds, deltas, and minerals that form in the presence of water. Clay minerals, sulfates, and other hydrated materials suggest that water once interacted with Martian rocks for long periods. The planet may once have had rivers, lakes, groundwater systems, and perhaps even temporary conditions that were much more hospitable than the dry desert seen today. NASA's Mars Reconnaissance Orbiter has mapped the surface in extraordinary detail, revealing ancient terrains shaped by water, dust, ice, impacts, and wind. The Curiosity rover has explored Gale Crater and found evidence that the crater once hosted a long-lived lake environment with conditions that could have supported microbial life if it ever existed there. The Perseverance rover has been studying Jezero Crater, an ancient lake basin with a preserved river delta, one of the most promising places to search for signs of past habitability. NASA's MAVEN mission, whose name stands for Mars Atmosphere and Volatile Evolution, has studied how the Martian atmosphere is being lost to space today. MAVEN is especially important for understanding the connection between the solar wind and planetary atmospheres. It has measured how solar storms can increase atmospheric escape from Mars, helping scientists estimate how the planet may have lost gas over time. The mission shows that the Sun is not just a distant light source. It can slowly erode the upper atmosphere of a planet, especially when that planet is small, weakly shielded, and unable to replenish its atmosphere strongly through geological activity. Mars is smaller than Earth, and that matters enormously. Its gravity is weaker, so it cannot hold gases as tightly. A lighter planet has a harder time keeping an atmosphere over billions of years, especially when upper atmospheric particles are heated, ionized, or struck by the solar wind. Mars also cooled internally faster than Earth because smaller planets lose heat more easily. As its interior cooled, its volcanic activity declined. With less volcanism, there was less long-term release of gases from the interior to help rebuild or maintain a thicker atmosphere. The Sun itself was also different in the deep past. When the solar system was young, the Sun likely produced a stronger solar wind and more intense high-energy radiation than it does today. Young stars are often more magnetically active, with more frequent flares and stronger particle outflows. This means early Mars may have faced a harsher space environment just when its atmosphere and surface water were most vulnerable. A weakening magnetic field during that era would have mattered greatly, because the planet was meeting a more energetic young sun. Over time, Mars became colder, drier, and thinner aired. As the atmosphere thinned, the pressure at the surface dropped. Liquid water became harder to maintain. Some water was lost to space after being broken apart in the upper atmosphere. Some became locked away as ice. Some may remain underground. Wind and dust became dominant forces on the surface, reshaping landscapes that water had once carved. The Mars we see now is not a planet where nothing ever happened. It is a planet where a more active past has been slowly preserved under cold dust. This is why Mars is such a useful comparison for Earth. It shows that a magnetic field can matter very deeply across geological time. It can help reduce direct interaction between the solar wind and a planet's upper atmosphere. It can influence how well a world holds onto gases, especially when combined with gravity, climate, chemistry, and geology. But Mars also teaches caution. A magnetic field is not a single magic guarantee of habitability, and losing one is not the only way for a planet to change. Earth is larger than Mars. It has stronger gravity, active plate tectonics, oceans, a thicker atmosphere, and a powerful geodynamo still operating in its liquid outer core. If Earth's magnetic field vanished, it would not become Mars in a single afternoon. The comparison is not useful because Mars offers a quick preview of tomorrow. It is useful because Mars shows what exposure, small size, weak gravity, reduced geology, and the solar wind can do over immense stretches of time. Mars is a lesson in patience. Planetary loss can be slow. Atmospheres can thin grain by grain, particle by particle, storm by storm. Water can disappear from the surface while leaving its signatures in valleys, minerals, and ancient lake beds. A world can change so gradually that no single day looks like the end, and yet after billions of years the difference is written across an entire planet. So when thinking about Earth without a magnetic field, Mars does not say that everything would instantly die. It says that shields matter most when time is allowed to work. The danger is not only the sudden storm, the damaged satellite, or the glowing sky. It is the long exposure, the patient erosion, and the quiet way a planet's relationship with its star can shape what kind of world it becomes. Mars is the obvious warning story, but it is not the only planet worth listening to. If Mars shows how a small world without a strong global magnetic field can lose much of its atmosphere over time, Venus and Mercury complicate the picture. They remind us that planets do not follow one simple rule. A magnetic field matters, but it is not the only thing deciding whether a world keeps an atmosphere, survives near the Sun, or becomes habitable. Venus is the first exception, and it is a dramatic one. It does not have a strong internally generated global magnetic field like Earth. There is no Venusian version of Earth's broad dipole field, produced by a deep geodynamo and stretching far into space as a large protective magnetosphere. If magnetic fields alone decided whether a planet could keep an atmosphere, Venus should be a stripped and airless rock. Instead, Venus has one of the thickest atmospheres in the solar system. Its air is dominated by carbon dioxide, with clouds made largely of sulfuric acid droplets, and the pressure at the surface is crushing. Standing on Venus would be less like standing under a normal sky, and more like being deep beneath an invisible ocean of hot gas, which is one of many reasons Venus remains a deeply unfriendly holiday destination. Its surface temperature is hot enough to melt lead, mostly because of an extreme greenhouse effect. Whatever Venus lacks in magnetic shielding, it has more than compensated for in atmospheric stubbornness. This does not mean Venus is gently protected. The solar wind still reaches it. Without a strong internal magnetic field, Venus interacts with the solar wind in a different way. The Sun's charged particles encounter the upper atmosphere and ionosphere of Venus. The ionosphere is a region where sunlight has stripped electrons from atoms and molecules, creating charged particles. This interaction creates what is called an induced magnetosphere. It is not generated from deep inside the planet like Earth's field, but from the way the solar wind and Venus's charged-up atmosphere push against one another. An induced magnetosphere can still provide some structure to the interaction between a planet and the solar wind. It can help divert solar wind around the planet, at least partly, and it shapes how atmospheric particles are lost to space. But it is not the same as Earth's internally generated magnetosphere. Venus is exposed in a different way, and it has almost certainly lost water over time. Ultraviolet light from the sun can break water molecules apart high in the atmosphere, and hydrogen, being very light, can escape into space. This may help explain why Venus is now so dry compared with Earth, and yet Venus has not lost its massive carbon dioxide atmosphere. That tells us something crucial. A planet's ability to keep an atmosphere depends on many factors: gravity, temperature, atmospheric composition, solar radiation, chemistry, volcanic outgassing, and time. Venus has enough gravity to hold onto a heavy atmosphere, and its carbon dioxide molecules are much heavier than hydrogen. It also appears to have had volcanic processes that helped build or maintain its atmosphere over time. The absence of an Earth-like magnetic field did not leave Venus bare. Mercury tells a different kind of story. It is the smallest planet in the solar system and the closest to the Sun. It receives far more intense sunlight than Earth and moves through a much stronger solar wind environment. One might expect such a small, scorched world to have no meaningful global magnetic field at all. But Mercury does have one. Mercury's magnetic field is global, but it is much weaker than Earth's. It is generated internally, likely by motion in part of its metallic core. This is surprising because Mercury is small, and small planets usually cool quickly. A cooled, inactive core would not easily support a dynamo. Yet Mercury's large iron-rich core appears to have remained partly molten or otherwise capable of maintaining magnetic activity. The result is a miniature magnetosphere, squeezed hard by the solar wind because Mercury sits so close to the Sun. NASA's MESSENGER mission transformed scientific understanding of Mercury. It orbited the planet and mapped its surface, measured its magnetic field, studied its composition, and revealed a world far more complex than a simple burned rock. MESSENGER confirmed details of Mercury's weak magnetic field and showed that its magnetic equator is offset from the planet's geographic equator, making the field unusually asymmetric. That asymmetry affects how the solar wind reaches the surface and shapes Mercury's tiny magnetic environment. The European Space Agency and the Japan Aerospace Exploration Agency are also studying Mercury through the Bepi-Colombo mission. Bepi-Colombo is designed to investigate Mercury's surface, interior, exosphere and magnetic field in greater detail. Its observations will help scientists understand why Mercury still has a magnetic field, how that field interacts with the solar wind, and what it reveals about the planet's deep interior. For a small world near the Sun, Mercury is a surprisingly rich laboratory for planetary magnetism. Mercury also shows that having a magnetic field does not automatically mean having a thick atmosphere. Mercury has only an extremely thin exosphere, made of atoms knocked from the surface by sunlight, solar wind particles, and micrometeorite impacts. Its gravity is weak, its surface is intensely heated by the sun, and it cannot hold a dense atmosphere like Earth or Venus. So here is the opposite lesson from Venus. A planet can have a global magnetic field and still lack a substantial atmosphere. Together, Venus and Mercury make the simple version of the story fall apart in a useful way. Venus has no strong internal global magnetic field, yet it has a massive atmosphere. Mercury has a global magnetic field, yet it has almost no atmosphere at all. Mars lost its global magnetic field and much of its atmosphere, but its small size, weaker gravity, cooling interior, and long climate history all mattered too. Earth has a strong magnetic field, a thick atmosphere, liquid oceans, active geology, and a favourable distance from the Sun. Each planet is a different combination of ingredients. Planetary magnetic fields vary because planetary interiors vary. A world may or may not have a liquid, electrically conductive core. It may rotate quickly or slowly. It may have enough internal heat to drive convection, or it may have cooled too much. Its core composition, pressure, thermal history, and mantle behavior all influence whether a dynamo can operate. Even when a magnetic field exists, its strength and shape depend on the planet's internal machinery and the external pressure of the solar wind. So Earth's magnetic field is important, but it is not a single magic answer to planetary survival. It helps protect satellites, shapes auroras, redirects charged particles, influences atmospheric escape, and makes Earth's relationship with the Sun gentler than it would otherwise be. But habitability is built from many overlapping conditions. Gravity holds the air. Chemistry determines what that air is made of. Geology can replenish gases. Oceans regulate heat and store carbon. Distance from the Sun controls how much energy arrives. Time slowly magnifies every advantage and every weakness. Venus and Mercury are reminders that planets are not simple machines with one switch labelled safe. They are layered worlds, each shaped by interior heat, sunlight, chemistry, gravity, and history. Earth's magnetic field matters because it is part of Earth's whole protective system. Not everything, but not nothing either. It is one quiet reason this planet has remained a blue, breathing world beneath a restless star. Earth's magnetic field can seem permanent from the surface, partly because human lives are so brief compared with the deep workings of the planet. A compass points, auroras shimmer near the poles, satellites move through a magnetically shaped environment, and it is easy to imagine the whole system as steady, fixed, and ancient in the simplest possible sense. But Earth's magnetic field is not frozen in place. It changes all the time. Those changes can be small, gradual, regional, or enormous. The strength of the field varies. Magnetic north drifts. Local features grow and fade. The field can become more complicated, less like a neat bar magnet and more like a restless pattern of overlapping influences. And, on geological timescales, Earth's magnetic field can even reverse, with magnetic north and magnetic south exchanging roles. The planet has done this many times before, with no need for dramatic music, although the rocks have kept the receipts. A geomagnetic reversal is an event in which Earth's magnetic polarity flips. In simple terms, the direction that a compass would recognize as magnetic north eventually becomes magnetic south, and magnetic south becomes magnetic north. This does not happen overnight. It unfolds over thousands of years, sometimes longer, as the geodynamo inside Earth reorganizes. During such transitions, the magnetic field may weaken, become more complex, and develop multiple temporary magnetic poles before settling into a new arrangement. The evidence for this comes from paleomagnetism, the study of ancient magnetic fields preserved in natural materials. When certain rocks form, magnetic minerals inside them can align with Earth's magnetic field at that time. As lava cools, for example, iron-bearing minerals may lock in the direction of the field like tiny compass needles frozen into stone. Sediments can also preserve magnetic signals as particles settle and become buried. Even the seafloor carries magnetic records, created as new ocean crust forms at mid-ocean ridges and spreads outward. This means Earth has been quietly recording its own magnetic behavior for millions and even billions of years. Rock becomes memory, lava becomes archive, the ocean floor becomes a long striped record of reversals, written not in ink but in magnetized minerals. It is one of the most elegant ideas in geology, the planet leaving notes for future scientists in the cooling of stone. One of the important figures in this story was Bernard Brunner, a French geophysicist working in the early 20th century. He studied volcanic rocks and found evidence that some ancient lava had been magnetized in a direction opposite to Earth's present magnetic field. This suggested that Earth's magnetic field had once been reversed. At the time, this was a remarkable idea. Today, reversed magnetization is a foundation of geomagnetism and paleomagnetism, helping scientists reconstruct the history of Earth's magnetic field. One of the most famous reversals is the Brunhes-Matuyama reversal, named for Bernard Brunhes, and the Japanese geophysicist Motonori Matuyama. It occurred roughly 780,000 years ago, and is the most recent full reversal of Earth's magnetic field. Since then, Earth has remained in the current magnetic polarity state, known as the Brunhes chron. That may sound like a long time, and it is, but in the language of geology it is not especially shocking. Earth has been around for more than 4.5 billion years, so 780,000 years is more like a recent paragraph than an ancient book. These reversals have been essential to understanding plate tectonics as well. On the seafloor, alternating bands of normally and reversely magnetized crust mirror one another on either side of mid-ocean ridges. This pattern helped confirm that new crust is created at ridges and moves outward over time. In that sense, Earth's magnetic reversals did more than reveal the history of the field. They helped prove that the surface of the planet itself is moving. The compass story became part of the plate tectonic story, which is a pleasing reminder that science often connects distant ideas when nobody is looking. It is also important to say what magnetic reversals do not appear to do. They do not appear to cause mass extinctions. The fossil record does not show a clear pattern of global biological catastrophes matching every reversal. Life has passed through many reversals before. Animals, plants, microbes, oceans, forests, and ecosystems have continued through these changes. That does not mean reversals are meaningless. During a weakened or complicated field state, the radiation environment and upper atmosphere may change. But the evidence does not support the claim that magnetic reversals are automatic extinction machines. There are also shorter and less complete events called geomagnetic excursions. During an excursion, the magnetic field may weaken and the magnetic poles may wander far from their usual positions, but the field does not complete a long-lasting full reversal. One of the best-known examples is the Lachamp event, which occurred around 42,000 years ago. During this event, Earth's magnetic field weakened significantly and briefly shifted in a dramatic way before returning to its previous polarity. The Lachamp event has attracted a great deal of scientific interest. Some research has proposed possible links between the weakened magnetic field, increased cosmic radiation, atmospheric chemistry changes, climate effects, and biological or cultural shifts. But these links remain debated and must be treated carefully. A weakened magnetic field can plausibly change radiation exposure and upper atmospheric chemistry, but connecting that directly to climate, ecosystems, or human history is much harder. Earth's systems are complex, and a good mystery should not be forced into a neat answer simply because the neat answer looks dramatic in a thumbnail. This is where the distinction becomes essential. Earth's magnetic field has changed before, it has weakened before, it has reversed before, it has wandered, flickered, and reorganized many times, but that is not the same as the sudden permanent disappearance imagined in the central question. A reversal is a natural reorganization of the field, not the total removal of Earth's magnetic environment. Even when the field weakens, it does not necessarily vanish completely. So the history of Earth's magnetism gives both reassurance and warning. The reassurance is that magnetic change is normal. Earth has passed through reversals and excursions without becoming lifeless. The warning is that the field is dynamic, not guaranteed in the exact form seen today. It is a living planetary process generated by deep motion in the outer core, and deep processes do not stay perfectly still. The rocks remember this better than human beings do. They preserve a planet whose invisible shield has flipped, drifted, weakened, recovered, and changed shape across ages too vast to feel. Earth's magnetic field is ancient, but it is not rigid. It is persistent, but not fixed. It is one of the great quiet motions of the planet, changing slowly beneath the ordinary world, while life continues beneath a sky that has never been quite as still as it seems. There is a place above Earth where the planet's magnetic shield is thinner than usual. It does not look dramatic from the ground. The ocean still moves, clouds still drift, cities still glow at night. People living beneath it are not walking around under a visible hole in the sky. But to satellites passing overhead, this region is important enough to be watched carefully. It is called the South Atlantic Anomaly. The South Atlantic Anomaly is a region where Earth's magnetic field is unusually weak compared with surrounding areas. It stretches over parts of South America and the South Atlantic Ocean, though its exact shape and position change over time. It is not a sharp-edged gap, and it is not a place where the magnetic field has vanished. It is better understood as a broad region where the field is weaker, allowing certain radiation effects normally held farther from Earth to reach lower altitudes. The reason this matters is connected to the Van Allen radiation belts. These belts are regions around Earth where energetic charged particles are trapped by the planet's magnetic field. They are not solid rings, and they are not perfectly even. Their shape is tied to Earth's magnetic field, which itself is not perfectly centered or perfectly symmetrical. Because Earth's magnetic field is offset and uneven, the inner Van Allen radiation belt dips closer to Earth over the South Atlantic Anomaly. This means satellites passing through the region can experience higher radiation exposure than they would in many other parts of the same orbit. The spacecraft is not suddenly flying into a wall of danger, but it may move through a zone where energetic particles are more likely to interfere with electronics and instruments. For satellites, that difference matters. Space hardware is delicate, expensive, and notoriously bad at popping down to the local repair shop. Energetic particles can cause several kinds of trouble. They can pass through electronic components and create single-event upsets, where a tiny burst of charge changes a bit of data or disrupts a process. They can increase background noise in detectors, making scientific measurements less clean. They can affect cameras, sensors, memory systems, and onboard computers. In some cases, spacecraft operators may turn off sensitive instruments while passing through the South Atlantic Anomaly to reduce the risk of damage or corrupted data. The Hubble Space Telescope, for example, has had to account for the South Atlantic Anomaly during its operations. The International Space Station also passes through the region, and radiation monitoring is part of life in orbit. Many satellites in low Earth orbit cross the anomaly regularly, depending on their path around the planet. For mission planners, the region is not a surprise. It is built into the way spacecraft are designed, monitored, and operated. NASA has studied the South Atlantic Anomaly for many years, using satellite data to track how the region changes. The European Space Agency's SWARM mission has also been important for measuring Earth's magnetic field in detail. SWARM consists of satellites designed to study the magnetic signals from Earth's core, mantle, crust, oceans, ionosphere, and magnetosphere. By measuring the field from orbit, missions like SWARM help scientists see how Earth's magnetic environment shifts over time. And the South Atlantic Anomaly is changing. It has moved and evolved, and some observations suggest it has deepened or split into more complex structure in recent decades. That sounds alarming if taken out of context, but it should not be treated as proof that Earth's magnetic field is about to disappear. The anomaly is real, and it is scientifically important, but it is not a countdown clock. Earth's magnetic field has always been uneven and dynamic. It changes because the geodynamo inside the planet changes. The geodynamo is the process by which motion in Earth's liquid outer core generates the magnetic field. Deep below the surface, electrically conductive iron-rich fluid moves under the influence of heat, buoyancy, rotation, and pressure. Those motions are not simple or perfectly symmetrical. They create a magnetic field that has broad global structure, but also regional variations. The South Atlantic anomaly may reflect unusual patterns in the magnetic field generated by the outer core, including areas where magnetic flux behaves differently beneath the surface. Studying the anomaly therefore helps scientists understand the deep interior of Earth, even though no one can visit the core directly. It is rather like listening to a muffled conversation through several thousand kilometers of rock and metal, then trying to work out what the speakers are doing. Magnetic measurements, seismic studies, laboratory experiments, and computer models all help build the picture. The South Atlantic anomaly gives researchers a real and changing feature to compare against models of core behavior. For people on the ground, the anomaly is not a major immediate danger. The atmosphere remains a powerful shield, and the increased radiation effects are most important at satellite altitudes. Someone walking through Brazil or sailing across the South Atlantic is still protected by the thick lower atmosphere overhead. The region does not mean sunlight is suddenly unsafe, or that the sky has developed a dangerous weak patch in the everyday sense. The practical concern is mainly for spacecraft, high-altitude systems, and the scientific understanding of Earth's magnetic field. Still, the South Atlantic anomaly is valuable because it offers a real glimpse of what weaker magnetic shielding can mean. It shows that even a regional reduction in field strength can matter for technology in orbit. It can influence how satellites are designed, how instruments are protected, how data are interpreted, and how spacecraft operations are planned. It turns the abstract idea of magnetic protection into something engineers must actually schedule around. It also reminds us that Earth's magnetic field is not a smooth, perfect shield. It has dents, strengths, weaknesses, and movement. It is generated by a restless planet, not by a polished machine. From the surface, that restlessness is easy to miss, but from orbit, the unevenness becomes measurable and sometimes inconvenient. The South Atlantic anomaly is not the disappearance of Earth's magnetic field. It is not a global crisis hiding over the ocean, but it is a quiet warning against imagining the magnetic shield as simple. Earth's field is alive with change. It can be stronger in one region, weaker in another, and altered over time by processes deep inside the planet. And in that weaker region above the South Atlantic, satellites experience a small preview of a harsher magnetic world, where invisible protection is thinner and space reaches a little closer than usual. If Earth's magnetic field disappeared, it would be very tempting to imagine humanity building a replacement. After all, people have built cities in deserts, tunnels beneath seas, telescopes in space, and machines that can land on Mars while being politely attacked by dust. Human engineering can be astonishing. So the question naturally appears, could technology step in and do what the planet's core once did? The honest answer is partly yes, but mostly no, depending on the scale of the problem. Humans could protect some things. Satellites could be made tougher, spacecraft could carry more shielding, power grids could be redesigned to handle stronger disturbances, astronauts could shelter inside better protected compartments during solar storms, sensitive electronics could be hardened against radiation, forecasting systems could give operators more warning when the sun became active. In other words, humans could adapt many individual systems to a harsher space environment. but replacing Earth's entire magnetosphere would be a very different challenge. The magnetosphere is not a small local shield placed neatly above one city or one satellite. It is a vast region extending far into space, shaped by Earth's magnetic field and constantly pushed and stretched by the solar wind. Recreating something like that artificially would mean building and powering a planetary-scale magnetic structure, one large enough to influence charged particles before they reach the atmosphere. That is not ordinary infrastructure. That is engineering at a scale so large it begins to sound less like a project and more like a polite request for physics to calm down. The more realistic approach would be targeted protection. Spacecraft already use several strategies to survive radiation. Some include radiation shielding materials, often using aluminium, specialized composites, or other materials placed around sensitive components. Shielding does not stop every particle, and adding more material can make spacecraft heavier and more expensive to launch, but it can reduce risk. Engineers also use radiation-hardened electronics designed to tolerate particle impacts better than ordinary commercial components. Satellites can also enter safe modes. A safe mode is a protective state where a spacecraft shuts down non-essential systems, points itself in a safer direction, preserves power, and waits for conditions to improve or for commands from Earth. This is not glamorous, but it is very useful. Sometimes survival is less about heroic action and more about turning things off before the sun gets ideas. Redundancy is another key principle. Important spacecraft systems often have backups, so if one component fails, another can take over. Error-correcting memory can detect and repair some data faults caused by radiation. Sensors can be shielded or temporarily disabled during dangerous passes through radiation-heavy regions. Satellite operators can plan around space weather forecasts, delaying sensitive operations during solar storms. None of this replaces a magnetic field, but it helps machines endure a more difficult environment. Power grids could also be made more resilient. Grid operators can monitor geomagnetically induced currents, adjust power flows, protect transformers, improve grounding systems, and develop operational plans for severe space weather. Stronger transformer design, better replacement capacity, and more accurate forecasting would all help. The National Oceanic and Atmospheric Administration Space Weather Prediction Center already monitors solar activity and issues forecasts that support these kinds of preparations. In a world without a magnetic field, such forecasting would become even more important. Astronauts would require different protections. Space stations might need storm shelters, small areas surrounded by extra shielding, water, supplies, or equipment arranged to absorb radiation. Water is useful because hydrogen-rich materials can help reduce certain kinds of particle radiation. Future spacecraft could be designed with protected sleeping areas or central compartments where crews could retreat during solar energetic particle events. Missions might need to be shorter, timed more carefully, or planned with stricter exposure limits. Human spaceflight would not necessarily end, but it would become more constrained and more expensive. There have also been speculative ideas about artificial magnetic shields for spacecraft or even planets. Some concepts imagine generating magnetic fields around a spacecraft to deflect charged particles, reducing radiation exposure during deep space travel. Other proposals have imagined placing a powerful magnetic shield near Mars, perhaps at a gravitational balance point between Mars and the Sun, to reduce atmospheric stripping by the solar wind. These ideas are interesting, and they show how seriously scientists and engineers take the problem of radiation and atmospheric loss. NASA's Planetary Science Division and wider space weather research communities study magnetic shielding, atmospheric escape, plasma physics, planetary habitability, and the way solar activity affects worlds. These fields overlap naturally because a planet's survival is not only about rock and air, it is also about particles, fields, chemistry, radiation, and time. Research into Mars, Venus, Mercury, Earth, and exoplanets all help scientists understand how magnetic environments influence planetary evolution. But artificial planetary shields remain speculative. Generating a magnetic field strong enough and large enough to protect an entire planet would require vast energy, enormous infrastructure, and a deep ability to control plasma interactions in space. Charged particles from the sun do not behave like ordinary wind hitting a wall. They are guided by magnetic and electric fields, interact with plasma, and change depending on solar conditions. Building a stable artificial magnetosphere around Earth would require more than simply placing a giant magnet somewhere overhead and hoping the sun respects the effort. There is also the problem of scale. Earth's natural magnetic field is generated by the motion of liquid metal in a core thousands of kilometers beneath the surface. The resulting magnetosphere reaches far beyond the planet and constantly adjusts under pressure from the solar wind. To imitate that artificially would mean recreating one of the largest natural protective structures associated with Earth. It would be like trying to replace the atmosphere with a fan, or the ocean with a bucket that has excellent intentions. So the practical future would almost certainly involve adaptation, not replacement. Humans would protect the systems most at risk. Satellites would be hardened. Spacecraft would be shielded. Astronauts would use storm shelters. Power grids would be reinforced. Aviation routes might be adjusted during solar events. Communication systems would need backups. Navigation would rely on multiple independent methods. Critical infrastructure would be designed with the assumption that space weather could reach more deeply into everyday life. This is not a hopeless picture. Humans are good at adapting to specific risks when those risks are understood. The danger is not that nothing could be done. The danger is imagining that one grand invention could neatly replace a planetary process billions of years in the making. Earth's magnetic field is not a device sitting above the clouds. It is a natural consequence of the planet's deep interior, linked to its rotation, heat, core composition, and long history. If it disappeared, humanity would not build a perfect new magnetosphere like a giant invisible umbrella. The response would be less elegant, more practical, and probably full of backup systems with very unpoetic names. But that is how survival often works. Not by replacing nature at full scale, but by understanding where the risks fall, protecting what matters most, and learning to live a little more carefully beneath a less forgiving sky. A world without Earth's magnetic field would not be a dead world. That is the first thing to keep steady in the mind. It would not be a planet where forests suddenly blackened, oceans vanished, birds fell from the sky, and every living thing looked upward with understandable disappointment. Earth is protected by more than one shield. The magnetic field matters deeply, but life on this planet has never depended on only one invisible barrier. At the surface, most life would likely continue in the short term. The atmosphere would still be there, held by Earth's gravity, thick enough to absorb and scatter much incoming radiation. Oceans would still cover most of the planet, and water is an excellent shield against many forms of radiation. Soil, caves, forests, buildings, burrows, and the bodies of organisms themselves would offer additional protection. Living cells also have repair mechanisms that can respond to certain kinds of damage, including damage to DNA. Biology is not helpless. It is messy, adaptive, and surprisingly good at continuing under conditions that would make a delicate machine file a formal complaint. But continuing is not the same as being unaffected. Losing the global magnetic field would make Earth more exposed, and that exposure would not fall equally everywhere. The greatest stresses would appear where the atmosphere is thin, where technology reaches upward, and where life depends on magnetic information. High-altitude environments would face greater radiation exposure than lower regions. Aircraft crews and frequent flyers could require more careful monitoring, especially during periods of strong solar activity. Polar ecosystems might experience changed radiation and atmospheric effects, depending on how charged particles entered the upper atmosphere without the usual magnetic guidance. Satellites would remain among the most vulnerable parts of modern civilization. With less magnetic shielding, spacecraft would face greater exposure to energetic particles from the sun and from deep space. Some would suffer more glitches, noisier sensors, damaged electronics, and faster degradation of solar panels. Navigation satellites, weather satellites, communication satellites, Earth observation missions, and scientific instruments would all need stronger protection or more frequent replacement. The world on the ground might still look calm, while the invisible infrastructure above it became more fragile. Electrical systems would also need greater care. Space weather can already disturb power grids under severe conditions because changes in Earth's magnetic environment can induce currents in long conductors. Without the global magnetic field, the way solar disturbances reached Earth would change, potentially increasing stress on exposed systems. The effect would not be the same everywhere. Grid design, local geology, transformer resilience, warning systems, and operational planning would all matter. But civilization would become more dependent on space weather forecasting, hardened infrastructure, and backup systems that could cope when the sun became unusually active. For animals, the loss would be quieter but still important. Many species appear to use magnetoreception, the ability to detect magnetic fields, as part of orientation or navigation. Migratory birds, sea turtles, salmon, lobsters, bats, bees, and some bacteria are all linked to magnetic sensing in different ways. Removing Earth's magnetic field would not erase all migration, because animals use many other cues. Stars, sunlight, smells, currents, coastlines, temperature, wind, memory, and learned routes would still exist. But species that rely heavily on magnetic maps, especially during early life stages or long journeys, could struggle. The ecological effects could ripple outward. If a migratory animal arrives later, takes a longer route, misses a breeding site, or becomes more vulnerable during travel, the consequences may spread into food webs. A disrupted migration can affect predators, prey, pollination, spawning, nesting, and seasonal timing. Nature is woven from relationships, not isolated creatures moving through empty space. A small change in direction can become a larger change in survival, reproduction, and ecosystem balance. Ocean life would have some protection that land life does not. Water absorbs many forms of radiation effectively, so organisms living beneath the surface would be partly shielded from increased particle effects above. The deeper the water, the more protection it offers. This does not mean ocean ecosystems would be untouched. Sea turtles, salmon, whales, plankton, fish, and many other organisms connect to the surface, the atmosphere, light, chemistry, currents, and migration patterns in different ways. But water would remain one of Earth's great protective layers, a blue shield beneath the sky. Life has also survived magnetic change before. Earth's magnetic field has weakened, shifted, and reversed many times across geological history. The fossil record does not show magnetic reversals causing repeated mass extinctions. That is reassuring, and it should prevent exaggerated claims. But a sudden total disappearance of the global magnetic field would be more extreme than a normal reversal or excursion. Natural reversals unfold over long timescales, and usually involve reorganization, not permanent absence. Losing the field entirely would mean removing a major part of Earth's usual interaction with the Sun. So, the realistic picture is not instant apocalypse. It is a living planet under greater strain. The atmosphere would still protect the surface. The oceans would still shelter life. Soil, caves, forests, and biological repair would still matter. But the upper atmosphere would face more direct particle impacts. Satellites and astronauts would face a harsher space environment. Aviation and high-altitude systems would require more caution. Some animals could lose a useful navigational sense. Electrical infrastructure would need better resilience. Future space-based civilization would become more difficult, more expensive, and more dependent on shielding. Earth would remain alive, but less sheltered. Its protection has always been layered. The magnetic field is one layer, the atmosphere is another. Water, geology, gravity, chemistry, biology, and time all add their own forms of defense. No single shield makes Earth habitable by itself. The planet is protected because many systems overlap, support one another, and reduce risk in different ways. Without the magnetic field, that layered system would lose one of its outer guardians. The world would still breathe, still turn, still grow, and still carry life. But it would meet the Sun more directly. It would become more technologically fragile, more exposed in its upper atmosphere, and more dependent on careful adaptation. Life would not end in a single dramatic moment. It would continue beneath a sky that had become a little less gentle. So what would actually happen if Earth's magnetic field disappeared? The answer is neither comforting fantasy nor instant disaster. Earth would not be destroyed in a flash. The surface would not immediately become lifeless. The atmosphere would not vanish overnight, and the oceans would not boil away beneath a suddenly hostile sky. But the planet would lose a major part of the invisible system that helps it live beside an active star. The result would be a world that remained recognizably Earth, but more exposed, more vulnerable, and more dependent on other layers of protection. The magnetic field is not a wall. It is not a solid dome. It is not a science fiction force field that blocks danger with a neat shimmer around the planet. It is a vast magnetic environment generated by motion in Earth's liquid outer core. It reaches outward into space, forming the magnetosphere, where it shapes the motion of charged particles from the Sun and beyond. It does not stop everything, but it redirects, traps, channels, and softens much of what would otherwise strike the upper atmosphere and near-Earth space more directly. Without it, satellites would likely suffer first. They operate above most of the atmosphere, in a region already filled with radiation hazards. Energetic particles could cause electronic glitches, damage solar panels, increase sensor noise, and shorten spacecraft lifetimes. Weather forecasting, navigation, communications, banking systems, emergency response, aviation, shipping, and scientific monitoring all depend on satellites in ways that are easy to forget, precisely because they usually work so quietly. Astronauts would face a sharper radiation problem. Low Earth orbit would become less protected, especially during solar energetic particle events. Spacecraft would need stronger shielding, better storm shelters, and more careful mission planning. Human spaceflight would not necessarily stop, but it would become harder, riskier, and more expensive. The higher humans travelled above the atmosphere, the more obvious the missing shield would become. Auroras would change too. The familiar polar displays are shaped by Earth's magnetic field, guiding charged particles toward the upper atmosphere near the Arctic and Antarctic. Without that magnetic structure, glowing skies might appear in stranger places and follow less familiar patterns. That could be beautiful, perhaps even breathtaking, but it would also be a sign of a more exposed upper atmosphere. The glow would not simply be decoration, it would be evidence of energy entering the air from space. Navigation would lose an ancient reference. A compass needle works by aligning with Earth's magnetic field. Without that field, magnetic compasses would no longer provide a reliable global direction. Modern systems would rely more heavily on satellite positioning, inertial navigation, radio systems, landmarks, maps, and the stars. Yet there is an irony there, because satellite navigation itself would become more vulnerable in the harsher radiation environment. Humanity would adapt, but one of the simplest tools ever used for direction would fall silent. Animals could also be affected. Magnetoreception appears in many forms of life, from migratory birds and sea turtles to salmon, lobsters, bees, bats, and magnetotactic bacteria. Magnetic sensing is not the only way animals navigate, but for some species it may provide important information during long-distance movement. Losing that signal could disrupt migration, breeding, feeding, and ecological timing. The effects would vary, but the loss of a planet-wide biological cue would not be trivial. On the ground, people would still be protected by the atmosphere. Sea level radiation would not suddenly match the radiation environment of space. Air, water, soil, and shelter would still absorb and scatter much incoming radiation. But high-altitude regions, aviation, polar areas, and the upper atmosphere would become more sensitive to solar activity. The ozone layer would not simply vanish, but atmospheric chemistry could be influenced more strongly by energetic particles during solar events. Power grids and long conductors could face greater stress from space weather, depending on infrastructure, latitude, geology, and preparation. Over very long timescales, the atmosphere could become more vulnerable to loss. Atmospheric escape is slow and complex, shaped by gravity, temperature, chemistry, solar activity, and geology. Mars shows how a planet without a strong global magnetic field can become more exposed to the solar wind. But Mars is also smaller, colder, and geologically different from Earth. Venus shows the opposite warning against oversimplification because it lacks an Earth-like global magnetic field and still has an enormous atmosphere. The magnetic field matters, but it's not a single switch labelled habitable. That is the central truth. Earth is not protected by one thing. It is protected by many things working together. Gravity holds the atmosphere. The atmosphere shields the surface. Oceans store heat, carbon, and life. Geology helps recycle gases across deep time. Biology repairs, adapts, and reorganizes. The magnetic field adds another outer layer, one born not in the sky, but in the deep motion of molten iron-rich metal thousands of kilometers below the surface. This makes the magnetic field strangely intimate. It is measurable by satellites, observatories, compasses, and instruments, yet it shapes conditions that feel completely ordinary. A working phone signal, a reliable weather forecast, a safe flight, a dark night under quiet stars, a bird crossing a continent, a planet keeping its upper atmosphere a little more protected from the sun. If it disappeared, Earth would remain Earth, but less guarded. The loss would be felt first in orbit, then in navigation, radiation exposure, space weather, atmospheric chemistry, and long-term planetary vulnerability. It would not be the end of life, but it would be the loss of a deep and ancient partnership between the planet's interior and the space around it. And perhaps that is why the magnetic field matters so much. It reminds us that ordinary life depends on invisible processes. The world is not only protected by what can be seen, touched, or breathed, it is also protected by hidden motion in the core, by magnetic lines reaching into space, by a quiet shield that never asks to be noticed. Earth turns beneath the sun, alive and exposed yet not entirely undefended. The shield is invisible, but the comfort it gives the planet is very real.